about 15 to 55 angstroms thick. And so if I have a piece of aluminum foil and I rip the aluminum foil, I will expose pure aluminum metal. But as soon as I'm ripping that piece of aluminum foil, an oxide will actually form on top of that. And that's about a 30 angstrom thick of aluminum oxide. And that's actually a good thing because aluminum could actually react in air and catch on fire, but it doesn't because it's formed this quickly protective oxide layer which passivates that aluminum and makes the aluminum underneath protected. We know that oxides aren't unique. We know that they exist for iron, like iron oxide and nickel oxide, and there's a whole host of elements that have oxides associated with them. But there are a few metals that do not form oxides. That's silver, gold, platinum, and that's why we make all of our jewelry out of these gold and platinum metals, because they don't form an oxide, they don't lose their luster. I think silver forms an oxide kind of slowly, but if you notice, we can always sort of polish that off and make our silver look good. And so, so these metals don't form oxides. And that actually is going to be a benefit to us when we actually try to do the atomic layer deposition of these metals that don't form oxides. The other thing that can happen to a surface, and this really happens in ultra-high vacuum, is that the metal atoms can actually relax. So we know that silicon surfaces, we have the bonds that are high energy, and they'll tip over and sort of bond with one another to lower the surface free energy. Well, metal bonds and ultra-high vacuum, if I take a metal surface and I cleave it, what's going to happen is that those few atoms on the surface, maybe 3 or 4 monolayers, are going to shrink, and they're going to collapse into the surface. And that really has to do with how a metallic bond is actually formed. And you know, obviously in the bulk, they stay the same, but the top surfaces relax. And that may have some advantages or disadvantages in the state of catalysis. But I just wanted to inform you that there is some sort of relaxation that happens with metals in ultra-high vacuum, and it can affect the electronic properties of the surface. Now, I'd like to get back to that physisorption well, and what it means to diffuse on a surface. So I've drawn here the energy of the vacuum. Everything above this vacuum line is basically the continuum, where a particle can take on any available energy states at once. But then as soon as it crosses that threshold of the vacuum level, it's now within the confines of the atomic potentials. And so here is a potential energy curve of cartoon, I should say, of a diagram of surface diffusion. So here's this corrugation, which would maybe be between atoms and atoms and site to site. And we're going to have this atom actually diffuse along the surface and go up over these humps. It's still going to stay on the surface, but it's going to hop from physisorbed well to physisorbed well to physisorbed well. And possibly it could actually jump over to a higher barrier and make a physical chemical bond with the surface. And that would be considered a chemisorbed well or a chemical bond with the surface. So what is the energy that it takes to actually hop over one of these little hills and one of these hills to get to the next valley? So the hopping energy, it can vary quite a bit depending on the surface. And it can be like 8 to 72 kcals per mole, which can be pretty big. But we can see that happen when we do atomic layer deposition, as molecules will actually diffuse on the surface before they actually react. So this surface diffusion, you can see, is temperature dependent. As I increase the temperature, I increase the energy of the molecules on the surface, and they can bounce around more quickly on the surface. And so if the temperature is too hot, then this molecule on the surface can actually desorb back into the continuum above the energy of the vacuum, or it could actually undergo a chemical reaction and fall into this chemisorption well and make a chemical bond with the surface. So surface diffusion is temperature dependent. If it's too hot, we can desorb molecules. We can also cause reactions to occur. So when we're talking about atomic layer deposition, we obviously want reactions to occur. So we need to have the temperature right in order to do that. Now, if we look at surface diffusion is the units of surface diffusion are given in terms of square centimeters per second. And so that is about the average area that a molecule will sample on a surface in 1 second. And obviously, if I increase the temperature, that value is going to go up, and I'm going to sort of sample more surface area per second. So a typical value for a surface diffusion constant is 0.0045 centimeters squared per second. And so just to calibrate you, what that means is that means that with that surface diffusion constant there, I sample a surface that's about 0.6 of a millimeter by 0.6 of a millimeter. So with that surface diffusion constant, that molecule that lands on that surface is just going to sort of go around and sample all that very small surface area by 6 millimeters by 0.6 millimeters. And so I leave that to you as an exercise to determine how many surface sites is in this 0.6 millimeter by 0.6 millimeter square, and then you have an idea when a molecule comes on a surface and diffuses with a certain diffusion constant, how many surface sites is this molecule actually sampling at a given temperature. And so if anyone wants to calculate that number, you can send it to us, and we could talk about it back on the webinar. All right. Now we've talked about surface diffusion, and the next thing I want to talk about is the chemical reactions. Now, if you're a chemist, if you're not a chemist, you may or may not know that chemical reactions proceed along a reaction coordinate. And there's two basic kinds of chemical reactions. There's exothermic chemical reactions, which actually emit heat when the reaction occurs, and there's endothermic chemical reactions, where they actually absorb heat in order for the reaction to proceed. So let's take a look at both of these. This is a plot of energy versus reaction coordinate. Now, reaction coordinate is a little bit vague. We're just sort of monitoring the pathway with which the reaction takes place. It's not necessarily an X or an Y or a Z reaction. It's sort of a physical chemical metric in order to watch a reaction take place. So in exothermic reaction, our reactants are at a higher energy state than the products. And so we have reactants here, and we can see that because that they're in a higher energy state than the products, that this is a thermodynamically favorable process. It may take forever to happen, but it's still thermodynamically downhill. And thermodynamics would call this process spontaneous. Even though it's not spontaneous per se, it will eventually, given the enough time in the universe, this reaction will take place. But what the barrier is between these reactions and products is this activation energy here, this hump that I've shown, and this, in order to get from reactants to products, you have to go through this transition state. So this transition state is a state that's slightly between the reactants and slightly between the products. So we will have reactants coming in, and they'll sort of both be bonded simultaneously, and some can fall back to the reactant state, and some can fall back down to the product state. So what we see here is that the difference between reactants and products is called the enthalpy, and if the enthalpy is negative, then I know that the reaction is downhill. I've also thrown in there delta G. Delta D and delta H are let's say they are proportional to one another. It's just that the delta G terms takes into consideration the entropy of the reaction. So if the products are more entropic than the reactants, like if the products are going out into the gas phase, then there's a little extra kick for the reaction to take place because I'm going to more entropy, and that's what the delta G term is. Now, endothermic reactions, you can see here that products are actually in a higher energy state than reactants. And so the enthalpy of reaction is actually positive, meaning that the reaction is not spontaneous and that we actually have to put energy into it or to pull energy in from the surroundings to get it to go. We still have a transition state that the reactants have to go through. And when we use atomic layer deposition, we really can't access these product states through ALD. But if we use a plasma, which is a very energetic gas, we can make products then that are part of an endothermic reaction in atomic layer deposition. So that opens up a whole new material class of compounds that we can make. Now this slide may be a little bit parochial, but I felt the need to go through it, is that there's 3 types of chemical bonding, and we have covalent bonding, we have metallic bonding, and we have ionic bonding. So we're really going to focus on covalent bonding and metallic bonding in atomic layer deposition. There's also literature out on making ionically bonded materials, which would be covered in a full class, the full short course program. So let's take a quick look at covalent bonding. And covalent bonding is basically a bond that has been created by 2 atoms sharing electrons. And so in this case, we have water, and we have hydrogen atoms here with 1 electron, and we have oxygen atoms here that can give up 1 electron. Now these 2 electrons will actually come together to form a bond between the oxygen and the hydrogen. And however, the main takeaway point here is that these electrons that these 2 atoms are sharing are not shared equally between the 2 atoms. And so if we see the oxygen is more electronegative than the hydrogen, and so the oxygen will actually take more of that electron density away from the hydrogen and become a little bit more negative than the hydrogen atom. And so the result of this electronegativity difference between the oxygen and the hydrogen is that a dipole gets created in the molecule. And so I've drawn that dipole here. So because of this dipole created in this molecule, then that will give this molecule certain properties. So as we know, water is a very good solvent, and it is this dipole that gets created that is actually enables water to have this polarity associated with it, and this solvating effect. So those are covalent bonds. Metallic bonds is where electrons are shared between all the atoms. So you have these positive ion cores that are actually swimming in this sea of electrons. And so normally there's this repulsive force between 2 positively ion cores. But if I add enough electron density between those positive ion cores really don't see each other very well. So they're not repulsed by one another because of the mediating electron sea that they all swim in. That's why metals are conducting, is because electrons can zig and zag and jake and juke all through the metal. It's not necessarily attached to one particular ion core. They're all sort of swimming around. The third is ionic bonding. This is really about like a sodium chloride. This is an electron transfer bond where an electron, there's a sodium which has a very terrible electronegativity. It hates electrons. It's more stable giving them up to something. And chlorine is much more amenable to having an electron on its atom. So when I have an electron transfer from an atom that hates electrons to an atom that gives electrons, they typically make an electrostatic bond. So I just wanted to go over the 3 types of chemical bonds in case there are any questions on that. All right, so the last concept that I want to talk about is the reactive sticking coefficient. So we talked about molecules coming down on the surface. We talked about they may go into a fizzy-sorbed well and they may bounce off. Well, this process is actually quantified through sticking coefficient. And sticking coefficient is given the letter S. So the question to ask yourself is, how many atom surface collisions do I need in order for a reaction to take place? Because a lot of those collisions will happen and a lot will bounce off. But some fraction of those colliding molecules or atoms will actually stay on the surface and be stuck in that fizzy-sorption well. Now, if they come down to the surface, they absorb in the fizzy-sorbed well, and then they go to the chemi-sorbed well, which is what we want in ALD, then it'll be this reactive sticking coefficient. So that's the probability that an atom will come down onto a surface and then actually react to form a thin film. So since sticking coefficient is a coefficient, it's between the value of 0 and 1. And so we really need this reactive sticking coefficient in determining the amount of chemical exposure in atomic layer deposition. And this really gives us an idea of how efficient the reaction is. So if my reactive sticking coefficient is 1,000, that means that it takes 1,000 atoms to come down on the surface for one of those to actually stick and react on the surface. So if the reaction is very, very efficient, it might have a sticking coefficient of 1, and all I need to do is bring down one atom onto a surface and it'll react. So I'm going to come back to reactive sticking coefficient in the future when we actually talk about how much chemical we need to perform ALD chemistry and run that to completion. The other thing I want to mention is that the reactive sticking coefficient is also important in increasing the step coverage inside a trench for chemical vapor deposition. And so if my reactive sticking coefficient is 1 or very, very high, and I'm trying to coat a trench, which I'm holding up my fingers, the molecules will come down and stick right on the edges of those trenches, and I'll get all of my deposition right on top of the trench and fall into this thing called a bread loafing, or it'll pinch off. But in chemical vapor deposition, if my reactive sticking coefficient is low, that molecule in the trench won't necessarily all collect at the top of the trench. It'll kind of ping pong down to the bottom, and then I can get a better, more conformal coating of a trench structure in CVD if I pay close attention to the sticking coefficient of my precursor molecules. So that's just as a side note, but reactive sticking coefficient is very important whether you're talking about ALD or also CVD. So that concludes the section on surfaces, and what I'd like to do is start to talk about vacuums and molecules for a few slides, and then I'll take a quick break and we'll assess the questions that people have already submitted. So vacuums and molecules. I know that this is probably maybe some rudimentary, but I'd like to get you calibrated in terms of the numbers we're talking about. And so the ideal gas law, which I affectionately known as PERV-NERT, relates the pressure and volume of a gas with the number of atoms and their temperature. Just simply that. So at STP conditions, standard temperature and pressure, temperature is 300 Kelvin, and the pressure is 760 torr, which is the pressure at sea level. Now I apply PERV-NERT, PV-NRT, and I'm going to solve for the concentration, the number of atoms there are. And when I solve this at standard temperature and pressure, I have the equation written down here. You can check my math if you'd like. I get 10 to the 19 atoms per cubic centimeter. So let's think about that. So here in your office, in my office right here, in 1 cubic centimeter, if I was at sea level and it was a very cold day, then I would have 10 to the 19 atoms just in that little cubic centimeter. So let's compare that when we did our calculation with water. With water, we had 10 to the 22 atoms per cubic centimeter. So this is the difference between liquids and gases, is 3 orders of magnitude. So we have liquids are about 10 to the 22 atoms per cubic centimeter, and gases are 10 to the 19th atoms per cubic centimeter. So there's a 3 orders of magnitude difference between the density of liquids and the density of gases. And so that comes into play like when you have an explosion or you have a molecule that's going to give off N2 gas as a reactive molecule. So you have a solid, which is 10 to the 22 atoms per cubic centimeter, and then that molecule explodes or reacts and gives off gases like CO2. They're going to expand 3 orders of magnitude and get to 10 to the 19th atoms per cubic centimeter. So just something to keep in your wheelhouse for back of the envelope calculations is the 3 orders of magnitude difference between liquids and gases. Now, that's not to say that number is always the same, because at 1 torr or maybe 5 torr or 3 torr, that's the typical pressure that ALD reactors are run, we get a value of about 10 to the 16 atoms per cubic centimeter in our little box. So it's obviously inversely proportional to pressure. So the higher the pressure, the more atoms we have in our cubic centimeter. Now, we have that box, that cubic centimeter box, and it's at a certain temperature. Now, all those molecules, that's just an average density of those molecules, because those molecules are zooming around in all different directions and are colliding with one another. So there's two primary concepts that I'd like to share with you about gas phases. And one is the Maxwell distributions of speeds, and one is the mean free path. So first, let's look at the Maxwell distributions of speeds. So in my cartoon over here, I have on the x-axis the speed of the molecule, and then I have on the y-axis the probability of occurring. So at low temperatures, I have that in blue, and you can see that the molecules are pretty well behaved. They exist in this nice envelope. They all have about the same speed, but there is a little bit of a distribution of speeds with the low temperatures of low temperature molecules in the gas phase. But then as I heat that gas up, we can see what happens to the distribution of the speeds. And so not only does the average speed move to higher speeds with higher temperature, but the distribution of the speeds actually increases as well. So again, at higher temperatures, the distribution of speeds increases as well as the average speed increases. And so that can be important. And sometimes in plasmas, where you have a very high temperature plasma, you get this high temperature wing of very highly energetic particles in your plasma because it's so hot that this has a tendency to damage the film because you have this little wing of very high temperature ions moving at such high velocities, smashing into your surface, and that's something you may not want. So with Maxwell distributions of speeds, this is the equation right here. Pi stands for 3.14159. And just to get you guys calibrated, if I have a cesium atom at 500 K, it's moving at about 175 meters per second. And I don't know about you, but that's extremely fast. That is moving very, very fast. I could try to convert that into miles per hour, or someone maybe on the other side could convert that into kilometers per hour. But that's a very fast-moving molecule in the gas phase at 500 K. The second thing I'd like to talk to you about, which is actually more important, is mean free path. Now, mean free path is exactly what it is. It's the average distance between two molecules in the gas phase. And so it's an average because some molecules are moving faster, some are moving slower. The distance between them isn't exact. It's just this average path. So notice that here's the mean free path equation. If I just take the mean speed and divide it by z, the collision velocity, I'll get the mean free path. But if I'm actually looking for the proper equation for it, I have that there on the right. And you can see that it's a function of the collisional cross-sectional area of the molecule. It's proportional to temperature. So as I increase temperature, I'm increasing the mean free path between molecules, but it's also inversely proportional to pressure. So as I increase pressure, as I add more and more molecules per centimeter squared, that mean free path is actually going to get smaller. And so mean free paths are actually very, very small. And just to get you folks calibrated is that the mean free path for an oxygen atom at room temperature in 1 atmosphere is about 70 nanometers. It's extremely small. So O2, maybe in your room, if you're filled with oxygen right now and you're at sea level, you have an average of 70 nanometers between all of those little oxygen atoms bouncing off one another. And you could probably calculate over here using the Maxwell distribution of speeds what the average speed is for those oxygen molecules. So these examples really enable us to really quantify what what's going on in the gas phase. So I said that mean free path was a little more important, and that is shown on this slide here. So the mean free path or pressure has different flow regimes. And so we have this, on one side, we have this laminar or viscous flow that we sort of are all familiar with in ALD reactors, but we also have something called molecular flow. And these two flow conditions are really dependent on the mean free path of the molecules in the gas phase. So the lower the pressure, the longer the mean free path. The shorter the pressure, the higher the pressure, the shorter the mean free path. So when we have a small mean free path, something here on the order of microns, that's a modest pressure regime, probably somewhere above a half of a torr. The distance between the molecules are small. The molecules run into one another. They exchange energy. And under a pressure difference, they all seem to flow in the same direction. And that is called viscous flow. And sometimes if I write the geometry, I get this laminar flow condition. And this is going to be very important in our ALD reactors, where they're about a pressure of about a torr, and we want to be able to transport chemical precursor very efficiently to our sample surface. And so we want to be in the laminar or viscous flow regime. Now, molecular flow is over here when the mean free path is actually very, very long. And this mean free path can be in the orders of inches or actually even feet. And so what happens in molecular flow is that molecules, as I've written here, go under this adsorption, desorption, adsorption process and never really run into any other of their beloved molecules in the gas phase. So here in the cartoon, we have atoms on a surface, and then they desorb, and they don't run into anything. They just go all the way to the other side of the chamber wall and then resorb. And then they desorb from there and then reabsorb on the other walls of the chamber. So you have this adsorption, desorption going on when the mean free path is actually larger than the chamber walls that contain the gas. And so there's no collisions of these molecules, or very few collisions of these molecules in the gas phase. And so the ultimate ideal of a large mean free path is deep space. And I've quoted values that the pressure of deep space is 10 to the minus 15 torr. So I encourage you on the other end, if you want to figure out what the mean free path is of molecules in free space, to see how long does a molecule have to travel in space before it runs into another molecule. I forget what that value is, but I think it's on the order of kilometers. So that's where we can also use these basic concepts of pressure and mean free path in order to understand parts of the universe. Now, we've got our laminar flow and our viscous flow, and those are the two extremes of flow. But there's also this transition region exists, and this exists somewhere between maybe 250 millitorr down to maybe 20 millitorr. This is a transition region that I would encourage you to avoid when you're running your ALD reactors, because it sort of has this turbulent flow, and it really can't make up its mind whether it's a viscous flow or a molecular flow, and it's a very challenging area to perform chemistry. But sometimes reactors need to be driven down just on the hairy edge of that transition zone in order to get our ALD chemistry to occur. One more thing I want to mention about mean free path is that I have a certain gas that has a mean free path on the order of microns, we'll say, but then I'm trying to coat this trench. And this trench is 200 angstroms, it's like 20 nanometers in diameter, which is much smaller than the mean free path of the gases above. So when molecules are actually trying to coat a trench in ALD, I'm actually going to be undergoing a molecular flow type condition inside this trench when the trench diameter is smaller than the mean free path of my ALD gas above that. So that's going to be important. And I'm not telling you that you can't coat these high aspect ratios or these very narrow structures. The key is that you have to wait enough time for molecular flow to take place for the ALD molecules to bounce down your trench, and then you have to wait enough time for the products of that ALD reaction to molecular flow and diffuse themselves back out of that trench and out. So the good news is that you can coat these large aspect ratios with very small trench sizes. The bad news is that the penalty you have to pay is actually the amount of time you have to spend for the ALD process to take place in these trenches. Now, another concept that I want to run past you, which is actually very important, is molecular flux. And I'm sure in your physics classes you've talked about flux or magnetic field flux. Well, this is a similar concept. Flux is just the number of atoms that cross a centimeter square window in 1 second. So I hope that you're seeing a general theme here is that we're boiling things down to centimeters squared. So we know that we have 10 to the 15 sites per centimeter squared. We know that we have 10 to the 22nd water molecules per centimeter cubed. But now I want to talk about a dynamic process of how many molecules are actually flowing through through a 1 centimeter squared area at a given pressure. So in 1 second. So flux is can be simply calculated by taking the concentration, which is pressure, multiplying it by, let's say, the average velocity that we've gotten from our Maxwell speed distribution, and dividing by 4. So the unit of flux are going to be the number of atoms or molecules per centimeter squared window size per second. And so at STP conditions, which is standard temperature and pressure, we get about 10 to the 23rd atoms that go through 1 centimeter squared in 1 second. 10 to the 23rd atoms per centimeter squared in 1 second at STP, at standard temperature and pressure. So let's use, and since we know, let's take a look at those flux values at different pressures, because we know at lower pressures that we're going to see the flux is actually going to go down. So at 760 torr, we get a flux of 10 to the 23rd atoms per centimeter squared. Now at 10 to the minus 6 right here, we get a flux of about 10 to the 14 atoms per centimeter squared per second. Here we go. So here, look, that flux value of 10 to the 14, 10 to the 15 is about the same order of magnitude as the number of sites there are on a surface per centimeter squared. This is a very important concept. The number of sites per centimeter squared are about 10 to the 15. The flux of atoms going through a centimeter squared surface at 10 to the minus 6 torr is about 10 to the 14, 10 to the 15. So we can start to be able to relate flux and the number of sites per centimeter squared, and this is going to become invaluable when we start to quantify the ALD surface chemistry. Now, if the sticking coefficient is 1, the pressure is 1 times 10 to the minus 6 torr, a monolayer of atoms will have covered that surface in 1 second. I hope that's clear. If the sticking coefficient is 1, I'm at a pressure of 1 times 10 to the minus 6 torr, a monolayer of atoms will have covered the surface in 1 second. And that is what's going to define something called the Langmuir. And the Langmuir is a unit of exposure. But if we go down in pressure, like 1 times 10 to the minus 10 torr, we're going to get at a very small flux, like 10 to the 10 atoms per centimeter squared per second. And so at a flux, at a pressure of 1 times 10 to the minus 10 torr, it takes 6 hours of time before a monolayer will cover a surface if the sticking coefficient is 1. 6 hours. So that's why experiments are done in ultra-high vacuum. If I have ultra-high vacuum, I cleave the surface, and from that point, I have 6 hours of time before I can do a delicate experiment on that unadulterated surface before a monolayer coverage of material will primarily carbon, will sort of contaminate that surface and not enable me to collect data on that surface. So at 10 to the minus 10 torr, you have about 6 hours of time before 1 centimeter squared is actually covered with material. Now let's drill down a little bit deeper into the unit of Langmuir. Now Langmuir quantifies molecular exposure. So really, what is the term exposure? So if I put myself in my refrigerator for a certain amount of time, I'm exposed to the cold. And that depends on how much time I'm in my refrigerator and how cold it is when I'm in my refrigerator. Now Langmuir, the unit of exposure, is the same thing, except it's the time a material sees a certain gas and the pressure of that gas. So this is an important concept, and it's an important unit in ALD chemistry. It's called the Langmuir. Now 1 Langmuir is going to equal 1 times 10 to the minus 6 torr seconds. And the reason being that at 1 Langmuir is when I get my surface is saturated with one monolayer of molecules in 1 second. That's the definition of a Langmuir. But ALD surfaces are really sort of defined by their reactive sticking coefficient. So if it's this is all assumed that the sticking coefficient is actually 1. But that's rarely the case in ALD. So here's a reactive sticking coefficient of 0.01. So now I'm going to need 100 Langmuirs of material before I reach surface saturation. And if the sticking coefficient is 1,000, then I'm going to need 1,000 Langmuirs of exposure in order to reach that same monolayer coverage. All right, and so at 1 torr with a sticking coefficient of 1,000, it's going to take about 16 minutes of time before I have that surface covered in a monolayer of molecules with a sticking coefficient that's very small. And so just to calibrate you folks on the other end about Langmuir, 100 Langmuir exposure is equivalent to 100 millitorr pulse for about a second. So if you're looking at your ALD chemistries and it needs 100 Langmuir, you can see that, oh, well, then I need 100 millitorr pulse for 1 second, and then I get my 100 Langmuirs. I hope that concept is clear. I'll be able to answer some questions about that. So the last concept I want to go over in our summary of surfaces and vacuums is vapor pressure. So liquids are always in equilibrium with the gases that actually exist right above the liquid surface. And so I've written that down as a chemical equation here, where the arrow is pointing more toward the liquid phase than the gas phase. But liquids always have, and solids, always have some molecules, some vapor molecules, right above their surface. So let's look at water for a quick example in the plot down to your left. And we can see that the vapor pressure on the y-axis and temperatures on the x-axis. So as I heat water up to 100 degrees C, I can see that the vapor pressure of water climbs and climbs and climbs until it actually reaches 760 torr, which is the pressure of air. And when that reaches that, then we actually see the water appear to be boiling. It's not boiling because it's hot. It's boiling because the vapor pressure above that water is equal to the pressure of the downward force of the atmosphere. So now if I'm in Colorado or I'm in the Rocky Mountains and I'm making tea and I'm only heating the overhead, the head pressure is less, and so I don't have to go up as high in temperature to like 80 degrees C to reach an equivalent pressure that pushes back against the outside environment in order for me to boil my tea. Mind you, my tea will be colder, but it will still be boiling. So this is the idea of vapor pressure. And this is actually very important because when we talk about liquid precursors and solid precursors, we're really going to need to manipulate the vapor pressure in order to get some of these precursor molecules into the gas phase and then into our reactor. So the vapor pressure is really defined by this Clausius-Clapeyron relationship, which is in a PChem text. And down below I have any of these, some examples of vapor pressures. And so we have water, which has a vapor pressure of 20 torr. Trimethyl aluminum, TMA, has a vapor pressure of 11 torr. This is very important because those are the two chemical precursors used in alumina ALD. Notice that they are relatively large in value. Iodine has a vapor pressure of 1 torr. Ionic salts, like sodium chloride, I think the vapor pressure is 0 because you're not really emitting one molecule of sodium and chlorine atoms. But I think that you can still boil that. And notice this selenium metal has a vapor pressure of 10 to the minus 11th torr. So even metals have a vapor pressure. So I have a metal, but I think it's just a metal. But even there is some small number of molecules of selenium metal that are actually basically leaving the surface. And so that's very interesting. And mercury is my last example because if you were a kid, you may or may not have blown it around on the desk with a straw and watch it disappear. And that has a vapor pressure of 10 to the minus 3 torr. So these are the concepts that I wanted to review with you that all are applicable to atomic layer deposition. And here's a quick summary of them, is that we have one surface site is 1 angstrom per centimeter squared. We have 10 to the 15 sites per centimeter squared on a surface. We have 2 typical energy regimes, a physisorption well and a chemisorption well. We talked about reactive sticking coefficient. We talked about flux, the unit of Langmuir, and we talked about viscous and molecular flow. So that concludes the fire hose session on surface and vacuum science. And I think what I'll do is let me check in with my assistant Amber here and see what kind of questions are available. And if there's nothing imminently relevant, I'd like to move on to the next section. So we'll take a quick breath right here.
I think if you want to open your Q&A,
okay. There's only a couple questions. Could I see your computer? All right, just a moment, folks. All right. Well, I think that I'll be able to answer these questions. Okay, I'll be able to answer these questions maybe at the next break, because I'd really like to move on to the next section. So let's take a look at the next section, which is really the most interesting, and this is the ALD surface reactions. And we're just going to push this through for the next hour, and then we'll take our proper 10-minute break. So ALD surface reactions. So I'm going to go over what are ALD surface reactions. I'm going to go over the advantages and limitations. We're going to sort of compare and contrast the thermal versus the plasma-based process. We're going to undergo a lot of examples of the single element process, which is very unique, binary compounds, which you already know and love, and then I'll do a quick slide on ternary elemental materials like barium strontiate and barium titanate and things of that nature. And then I have one slide on the molecular layer deposition. So in order to understand what ALD surface reactions are, it's best to compare and contrast those with other thin film deposition techniques. So I'm pointing out 3 deposition techniques here. These are techniques on how to deposit a thin film. We have evaporation, we have sputtering, and we have this molecular beam epitaxy. And so you might be familiar with one or all 3 of these techniques. Evaporation is just when I have maybe a piece of tantalum flow or a tantalum boat, and I put a low melting point metal in there, and I run electric current through it, or I heat it up, and we get molecules that increase their vapor pressure, and they go into the gas phase, and then they deposit on a colder sample substrate that might be mounted right above the sample. This is typically a line of sight technique where molecules will just leave and then ballistically go and then just stick wherever they hit. Another similar method to that is sputtering. And sputtering is sort of a more aggressive method of evaporation, where we'll have a sample mounted on the top, and we actually have sputtering targets that are made of certain elements or compounds, and we bias those targets. And so if we're going to use argon to sort of accelerate the argon ions down to the sputter target, and then we're going to eject the material on the sputter target, and the flux of that will actually then redistribute itself on the sample. We can use argon atoms and negatively bias the sputter target with a negative bias, or we can actually, this also is done with electrons, where we have an electron beam and we positively bias the sputter target and accelerate electrons into the sputter target, and that ejects the material from the sputter target and then deposits on the sample. Again, this is a slight line of sight deposition technique, but there's very exotic ways of taking your samples and mounting them at angles and rotating and spinning them so that you get better uniformity, and you get maybe coating some trench-like structures if they're not too big. The third technique is molecular beam epitaxy, and as you can imagine, that this is an epitaxial technique where the atoms actually fit within registry of one another. And what MBE is really done at very low pressures, because we want these long mean-free paths, because we want the reactions to happen only at the surface. We don't want them to happen in the gas phase. So we have these low pressures, these long mean-free paths, and obviously we have these very low flux numbers. And so because these atoms coming out of either A or B or C, the chemical reactants onto the surface, have such low fluxes, then we do have this atomic layer control of thickness. But again, it takes a very long time to grow these samples. But what you can grow with molecular beam epitaxy are very, very interesting quantum well and superlattice structures that are very interesting solid-state physical electronic properties. And so these are three basic gas phase deposition techniques. I couldn't walk away with talking about deposition techniques unless I mentioned some of the solution-based electrochemical methods. And so here's a good technique for depositing copper or other materials. So we can deposit thin films by the gas phase, or we can do it by electrochemical methods. Now there's one more method that's actually very closer to ALD, and that is chemical vapor deposition, or CVD. And so on the surface, chemical vapor deposition just deposits film by reacting a mixture of gases over a hot substrate. But there's a little bit more detail in that. In chemical vapor deposition, we bring in the reactants simultaneously. They go through the same shower head, the same piping. We mix them up, and they mix before they get to the hot substrate. So if we sort of broke the CVD process down, we would have this region A where we have this nice mixing of gases, and then we have this region B. And this region B is very important to point out, is that we get these reactions in the near surface region. The substrate is hot. It has enough energy to actually make these some of these gas phase molecules actually react with one another, and as they react, then they come down onto the surface and probably react even more on the substrate. Or you can have some of these individual molecular gases absorb on the surface and then react. But CVD has this unique feature where you get surface reactions in the near surface region. And I'm pointing that out because ALD does not have these reactions in the near surface region. So that's one of the two primary differences in CVD, is that you get this near surface reaction reaction take place right above it. Now, the fourth step would be that there are gas phase reaction products that either leave the surface or can actually get incorporated into the film. And what we can do with CVD is that we can change the film stoichiometry by really putting a lot more of one gas in than another. We can change the properties of the film, the structure, all by just changing the reactive precursor flow of each of the individual reactants. And that would be essentially the flux. And also we can change the structure and properties of the film by changing the temperature. I'm giving you this silicon nitride example here. This is the stoichiometry of the silicon nitride. It's the chemical equation. Notice that we give off 10 hydrogen atoms per few moles of these, per 1 mole of the silicon nitride being formed. And by doing so, if our reaction temperature isn't hot enough, we will include a lot of this hydrogen in the film. So the CVD of silicon nitride typically happens at a lot higher temperature. One thing to note about a CVD reaction is that there's really two different kinetic regimes in a CVD reaction. When this substrate is so hot that everything that comes down onto the surface will react and form a film, then we're sort of in the mass transport limited regime, where the temperature is so hot, it doesn't matter how hot it is, it's just hot, and the number of molecules that I come into the surface actually react on the surface, and the film thickness grows at a rate of how much I bring in the chemicals, how quickly I bring in the flows or the flux of the chemicals. The second regime in CVD is really the kinetic regime, and that's at a lower temperature, where I have a bunch of these gas phase molecules sort of on the surface in the gas phase, and they're constantly being pumped out. But the kinetics of the reaction are actually determining the growth steps of the regime, the growth of the film. So those are two different regimes in the CVD process. So CVD, we know that we bring these reactants in simultaneously. We know that there's a near surface region of chemical reactivity right above the substrate surface. So now let's contrast that with the ALD process. So here's the cartoon of the ALD process. So the primary difference between chemical vapor deposition and atomic layer deposition is that in CVD, we bring the reactants in simultaneously, but in ALD, we bring the reactants in sequentially. So because we bring the reactants in sequentially, now we have these two half reactions of the chemical reaction. So we break this CVD chemical reaction up into two half reactions, typically denoted A and B. And so here's a cartoon of the ALD type process. It's typically a 4-step sequence where I have a surface here, 1, and I bring in X, and I have X react on the surface, and I produce byproducts. And so then the step 2 would be that I have an inert purge gas where I remove all the X from the reactor, I remove all the products from the reactor, and when that step is complete, then I move on to the B reaction where I bring in reactant Y. Reactant Y reacts with the precursor X on the surface and produces products. And when that reaction is complete, then I go to my 4th purge step and I remove all the Y reactant from the reactor and all the products, and then I go and I repeat. So in atomic layer deposition, when I run these AB sequences, these half reactions, then I'll actually see a film grow. Now what's important is that each one of these half reactions really puts down less than a monolayer of coverage per half cycle. So I'm really not growing single crystal unit cell films at a time. I'm growing, partial monolayers of films at a time. So that's why we'll see these growth rates. I shouldn't call it growth rate. It should be growth per cycle of about 0.2 of an angstrom to 4 angstroms of film growth per AB cycle. So these films, because we're only growing partial monolayers at a time, these films are typically amorphous, or else they may convert into a polycrystalline form. So these films aren't single crystal, and they're grown at a much lower rate than what putting down unit cell by unit cell. But really what makes this ALD chemistry work is this self-limiting surface reactions of this step that enables the stepwise process of ALD. So let's talk about that momentarily. So self-limiting surface reactions. This is the word that you need to know for ALD chemistry. ALD chemistry shows the self-limiting surface reaction behavior. So what does that mean? So when molecules come down and react on a surface, they're going to produce a new surface. But that new surface will not react with any of those incident molecules coming down onto the surface. And this is considered a self-limiting surface reaction. And this is vital. This is critical to the process of ALD. So here in my cartoon, we have a hot substrate. We come down with X. They react on the surface, but we don't build a multi-layer of material on this surface. They just react on the surface and then they stop. And that is the self-limiting behavior of the surface reaction. So once the surface is saturated, we can proceed with the pump out plan and know that the surface has as much of this A reaction as possible. Then when they're all pumped out, I can come down with the B reaction. The B reaction comes in and reacts with the A surface, but no more. It doesn't react with anything else on the surface except what the A reaction is left behind. And so then once that reaction has taken place, no other precursor chemistry will happen, and then I'm allowed to pump that B reaction out. And so then as I do the AB kind of sequence, then I get this film to grow. So the chemistry between the surface and the gas phase precursors really determine what gets deposited. So these are sort of cartoons, but now let's look into more detail of an actual example of ALD. So here's the example of titanium oxide ALD. We take titanium tetrachloride and water, and we bring them into a chamber, and we react them simultaneously in CVD, and I make titanium tetrachloride, and I make hydrochloric acid. So this reaction is downhill. It's the delta H is pretty negative. And so this is the cartoon of how this actually takes place. The first thing that I have to assume about this is that my A reaction, I've got this hydroxylated surface. I've got this OH surface, this OH saturated surface. So when I come in with titanium tetrachloride, I can react 1 or 2 of those chlorine atoms with the hydrogen of the OH on the surface to make an O titanium bond and give off HCl gas, and leaving you with a chlorinated surface. That's what happens in the A reaction. Now, if I bring down more titanium tetrachloride onto this chlorine surface, it's just not going to react for the same molecules. Now, I take this titanium chloride surface in the product in the A reaction, and I apply it to the B reaction. So here's the reactive surface in the B reaction, and I come in with a water pulse. Now that water is going to react with all of that chlorine that's on the surface. And so when it reacts with that, it's going to rehydroxylate the surface right here and make HCl gas. So the most important thing to recognize here is in this note is that the product surface of the B reaction, these OHs, is the reactant surface in the A reaction. So this enables me to run this in an AB-AB-like sequence. So this product surface in the B reaction, I can now use as my reactive surface in my reactant in my A reaction. They'll now react with the titanium tetrachloride. So that's really what makes this chemistry drive. So let's go through another example of that, and that would be aluminum oxide deposition. So here's aluminum oxide, CVD. It's aluminum oxide, trimethyl aluminum and water makes aluminum oxide and actually produces methane as a byproduct, which is pretty interesting because methane itself can be burnt for fuel to make tea. So, and this has a very large delta H of reaction. So let's take a look at reaction A. Again, we assume that we have this hydroxylated surface. We come in with trimethyl aluminum. Trimethyl aluminum reacts with the OHs on the surface, and we make an O-Al bond, and we have this methyl terminated surface here on the product of the A reaction, and we produce methane gas. So once all those surface sites are reacted with, any additional TMA onto the surface will not react with these methyl groups. And so we know that the reaction's gone to completion. Now we take that product surface in the A reaction and apply it to the reactive surface in the B reaction. And here I have this methyl terminated surface in the B reaction. I react that with water. I hydroxylate the surface. I remove all those methyl groups to make ALO bonds again and methane gas. And so here we go. Again, we have the product surface of the B reaction is the reactive surface in the A reaction. And again, this enables us to run the AB-AB-like reaction sequence repeatedly to make a thin film to grow. Now notice that I've left the exact surface chemistry stoichiometry vague, whereas in CVD I can write actual reactants and products, and I can balance, I can do the mass balance of either side of the equation. In ALD, the chemistry is left relatively vague. So if you see it in the literature, I wouldn't belabor that point, but just get that the chemistry is there. And also, the binary reaction sequence makes sense in this AB-AB format to put down materials that have two components in them. So if I have aluminum oxide or titanium nitride, I'm putting down two elements in my film and I'm running it in two AB-AB reactions. So that really sort of makes sense in this AB-AB sequence. So now let's take a quick look at the aluminum oxide ALD reaction in a little more detail in terms of the physical chemistry of it. So here's the potential energy diagram for the aluminum oxide reaction. And I start with this hydroxylated surface, and I come down with this dose of trimethyl aluminum. And notice that we fall into this slight physisorption well right here with the aluminum making a slight interaction with probably the non-bonding electron pair of that OH on the surface. This is this physisorption well. And then as I start to move up the potential energy diagram to the transition state, I can see that I'm sort of quasi-bound. I make an aluminum-oxygen bond that's kind of happening, but I'm also sort of leaving that aluminum or that oxygen-hydrogen bond is also sort of getting weaker. And so as this happens, I fall downhill to the more thermodynamically stable bond, which is the aluminum oxygen bond, and then my H is probably formed as H2 and leaves as a byproduct. Here I've fallen down into the chemisorption well. So I went from the physisorption well up through the transition state and then down into the chemisorption well to put my ALD precursor, my trimethyl aluminum, onto my hydroxylated surface. This is the A reaction. Now there's a similar potential energy diagram for the B reaction. Here's my methylated surface. I'm coming down with water. Waterfall, it gets physisorbed onto the surface and sort of makes this bond here, probably again with the non-bonding electron pairs of the oxygen seeking the nucleus of the aluminum atom. And as that is in equilibrium, I start to march up the transition state, and aluminum would much rather be bound to oxygen than the methyl group. And so then this transition state moiety falls down into the chemisorption well. I make the aluminum oxygen bond, and then I leave methane into the gas phase. So a typical reactive sticking coefficient for aluminum oxide is about 10 to the minus 3. So this is sort of the potential energy diagram of how an ALD process actually takes place, and the numbers on the y-axis are pretty close to what they are in reality, according to simulations. Now, I mentioned that we reach this self-limiting behavior of these reactions, and sometimes there's an ideal self-limiting, and sometimes there's something called soft saturation. So on this plot to the left, I have the number of atoms absorbed on the surface as a function of chemical exposure in L, given in Langmuir's. And so as I add chemicals to the surface, they all get absorbed onto the surface. And then in an ideal world in ALD, the more chemical precursor I add to the surface, I don't necessarily add any more atoms to the surface, which is given by this green line right here. So this would be the ideal self-limiting behavior of atomic layer deposition. But you're going to notice in the literature that some people quote certain angstroms per cycle that are different. I know that titanium oxide is one of them. And so what we can have there is a softer saturation. And that's that we come up on the curve with the number of atoms absorbed on the surface. But as we increase the chemical exposure, possibly maybe if we add orders and orders of magnitude more chemical on the surface, we'll actually start to get more atoms absorbed onto the surface. And this is called a soft saturation. So if you're running your ALD with a lot of chemical precursor, depending on what the precursor is, you could be somewhere up in this soft saturation zone, and you'll quote a different growth per cycle, per AD cycle, than somebody else. And so for some chemicals, it's an order of magnitude difference up here in the soft saturation, and other times it just could be a factor of 5. So one of these chemistries is hafnium oxide. I know that hafnium oxide has a relative soft saturation. So if you add a lot more chemical to a lot more chemical precursor, you'll probably start to fill in some of those other some of those reactive sites on the surface with a lot more chemical exposure, and then you'll get more atoms on the surface, which will give you a greater growth per cycle. So I've tried to sort of identify those in these cartoons I've shown on the right. So this soft saturation can lead to variability in the quoted ALD growth rates per cycle. And ALD chemistry even has a varying degrees of this soft saturation. Alumina being our most ideal ALD chemistry, even that will show a little soft saturation if I really hammer that surface with a lot of chemical precursor. So let's talk next about this ALD temperature window. So ALD doesn't exist at all different temperatures. There's a certain window of temperature for each unique process where this ALD chemistry can take place. So here I have on the y-axis this growth per cycle, and the x-axis is temperature. So when the temperature is too low, we can see one of two things occur. We can either see that the growth per cycle actually goes down, or the growth per cycle actually will go up. So these are two different scenarios that happen on the surface. If the temperature is too low, and I'm seeing this very large growth per cycle, I could actually get ALD chemical precursor to sort of condense into a liquid or a solid on the surface. So as I do my AB cycles, I'm actually seeing a larger growth per cycle, as temperature goes down, because I have more of this liquid or this solid that I've sort of condensed onto the surface. The opposite of that is that there's just not enough thermal or kinetic energy to make the reaction drive to completion. And so when the temperature is too low, I get a very low growth per cycle because of an incomplete reaction, because there's just not enough thermal energy for the reaction to get over the activation energy into the transition state and into the the chemisorption well. Now the same exists with being too hot. Now I mentioned in the CVD that we can make our sample very, very hot, be in the mass transport limited regime, and every molecule that goes in is going to react on that surface. But in ALD, if we're too hot of a surface, our precursor molecule can come down on the surface, decompose, and sort of poison our surface, or we actually just start to build a multi-layer of decomposed products on the surface as I do my AB cycles. And that's when the temperature is too hot. Or I can decompose and then I just sort of desorb all my surfaces, species from the surface. If my temperature is too hot, the precursor that comes down, maybe I need that precursor to be in a physisorbed well, but it's too hot, and that precursor just desorbs right away. So I'll see a decrease in the growth per cycle as a function of temperature if I'm too hot, if I'm outside the temperature window. So these are the two regimes of ALD, and this temperature window can vary wildly between different chemistries. Alumina ALD has a very large temperature window. You can do it basically at room temperature or or hundreds of C, whereas maybe platinum ALD has a very low temperature window. If you're too hot or you're too cold, it just won't run. It might have a 20 to 30 degree window, thermal window. So the ALD window is an important concept to understand, and also know that the ALD window varies from chemistry to chemistry. Now, let's take I've listed the advantages and limitations of ALD chemistry, and we'll just go through those. So it's because of this self-limiting behavior that I described that for each of these ALD cycles that really give it its unique advantages. So the first advantage of this self-limiting behavior is that I can control the thickness of the film by performing the desired number of AB cycles. So if I needed 18 angstroms, I can give you 18 angstroms. If I need 320 angstroms, I can dial in 320 angstroms of this film. I mean, it's absolutely remarkable compared to the other deposition techniques that I've covered, that you can have this really acute control of thickness. The next, probably as equally if not more important advantage of ALD is that it can conformally coat these high aspect ratio structures. So no other technique can get into a very small trench and put down the same thickness of material from the top to the bottom. I mean, it's a remarkable technique. If you're in the stone age of CVD or sputtering, this is just like a brand new day. So it's very exciting. And if you look at the aspect ratios of, that's the length of the trench divided by the diameter of the top, you can get things, that should be a +3, sorry about that. That you can code aspect ratios of 10 to the 3, which is a remarkable achievement for a certain chemistry. It opens up all sorts of application space. So these can be pores or trenches or tortuous paths, even non-line of sight deposition. You can get your chemistry in up under a shelf, and you'll get the same thickness there as you will on the surface. Now, mind you, that when we're coding high aspect ratios, the amount of flux, the amount of exposure on the surface is going to be higher than it is down in one of these trenches. So you might see a little thicker film growth on your surface than you would down in this trench, just because of the sheer amount of chemical exposure and the soft saturation of the chemistry. Now, the other advantage of that the reaction temperatures of ALD chemistries are typically lower than their corresponding CVD reactions. And this is both good and bad. It's good in the sense that we can coat materials with at lower temperatures, so that opens up the space of coating polymers or other materials that are sensitive to temperature. It also produces no particles, whereas CVD, those chemicals are reacting on the hot substrate or in the near surface region, and if they don't get deposited on the surface, then they'll generate particles in the reactor. And if you talk to anyone in the semiconductor industry, particles are really sort of the bad news, and they're difficult to get rid of. So in these ALD chemistries, we really don't have any particle formation as long as our pulse and our purge steps are an adequate length in order to sweep all the precursor out. The last advantage that I see in ALD chemistry is their ability to investigate the nucleation of a thin film. Now, the other deposition techniques, they just came down and they sputtered the film, or they deposited relatively rapidly. But because ALD is sort of doing this stepwise, one half cycle at a time, you can watch a surface physically evolve from what the substrate was into the deposited film. And I think that's a very powerful technique, because as devices get smaller and smaller and interfaces become more and more important, we're really going to need to understand what those interfaces are, and those interfaces are really what happens as a film nucleates on top of another film. With that motivates this slide, is that everything that I've talked about is really growth. I've talked about depositing one material on the same type of material, and that's why I had you assume that there were these oxide handles on the surface, because that was our reactive handle on the surface. And so when we talk about growth, we already assume that the ALD chemistry can take place. As I mentioned, that typical growth rates can be like 0.4 of an angstrom per cycle, up to 4 angstroms per cycle, depending on the chemistry. ALD films are typically amorphous or polycrystalline. So now let's talk about nucleation. Nucleation is depositing one material on a different type of material. So that different type of material may not have these nice hydroxyl groups to nucleate on. It'll have a different chemical structure. It'll have a different electronic structure. So how chemistry nucleates on those surfaces is going to be very different than growth. And so if you study nucleation in ALD, it'll tell you that there's very dramatic differences between nucleation chemistry and growth chemistry. So nucleation rates, or the number of cycles it takes to actually nucleate an atomic layer film on top of a film, can be up to 1 to 40 ALD cycles, just to form that initial ALD monolayer where growth can take place. So I might have to run my AD chemistry 40 times before I actually get enough of that chemistry on all those surface sites to make a monolayer of my growing film, and then I'm off to the races, and then I can see, then I'm in the growth regime where the AB chemistry makes more sense. ALD nucleation isn't necessarily well understood, but it can be studied with ALD chemistry by doing a half cycle, analyzing the surface, doing the next half cycle, analyzing the surface, and watching the film evolve from your substrate to the deposited film. And I think that's a very interesting area of research. One implication of nucleation is that the more nucleation cycles it takes to nucleate a film, the rougher the film is going to be. So if you really try to get these very smooth films, you'd like things to nucleate within 1 or 2 ALD cycles, and then your film will be very, very smooth. So as these devices in our day and age get smaller and smaller, interfaces are going to become increasingly important, and it's going to be increasingly important to really understand the dynamics that happen and the bonding that is occurring at the nucleation phase of the thin film growth. So some of the limitations of ALD, I have them listed here. And so the properties of the ALD grown films are different than our CVD analogs or our sputtering analogs. So this is really important. And it just has to do with how the process is run. As we know, the CVD can be very, very hot. We have deposition, we have reactions in the near surface region. But ALD, we bring them in sequentially. We don't have a near surface region reaction. We can never get an ALD chemistry too hot, or else we'll see decomposition. So the ALD films are different, have different properties than the conventional films. So that's really important to take into consideration, especially like if you've been relying on a film for a specific process and you want to move to that equivalent ALD process, that ALD film might not have the same properties that you're looking for. The second thing is it takes a lot of time to grow a thick film. I mean, with growth per cycle of about 1 angstrom per cycle, you really can't grow 10 microns of material, 10,000 angstroms at a time. It just takes too much time. And so you might not want to use this in all your applications. So if you can either increase the cycle time, or if you can make your device smaller, then you're in the ALD space. But you just can't grow a thick film with ALD. It just takes too much time. Generally, there's not a selective deposition, but that area selective ALD conference that's happening at the end of April is starting to really chip away on this active area of research. And so typically you coat everything whether you like it or not, but they're really starting to drill down into the details of the surface chemistry and coming up with these selective deposition ALD techniques. So that's a very exciting area of research. Films are typically polycrystalline or amorphous, as I've mentioned previously. There's no high temperature ALD like there is for these high quality CVD films. So CVD, I can make that film, I can have that substrate very, very hot. But in ALD, there's an upper limit to the temperature which I can run in ALD chemistry. And that will limit its properties and make them different than what we might see in a CVD film. Precursor vapor pressures limits the type of reactants. So there's all sorts of materials we can deposit with ALD, but that really comes back to the type of precursor that we use, whether that's a solid, a liquid, or a gas. And if it's a solid, we need to get that vapor pressure up and into the reactor to have it undergo ALD chemistry. And so there's all sorts of chemists, organic, inorganic chemists, organometallic chemists, working on new precursors that have high vapor pressure, that are stable, thermally stable, and perform the ALD chemistry that we're looking for. And also the last limitation is that it's pretty challenging to control or tune the stoichiometry of the film. We're really only limited by what happens on the surface to determine what the stoichiometry is, whereas in CVD, we can bring in 10 times as much ammonia versus silane to make silicon nitride, or we can tune the flow. We really can't tune the flow in ALD in order to tune the stoichiometry. So you kind of get what you have with the ALD deposited film, because that chemistry only happens on the surface. With all those primary limitations said, this is a very important technique to keep in your scientific toolbox. Okay, so I'm going to, that ends this section. So now I'm going to move on to plasma. Oh, yeah. So here we are with plasmas. And so everything that I've talked about so far is thermal ALD. It follows chemical kinetics and thermodynamics. It has, I've shown the reaction coordinate here and energy. Reactants follow the products. We have this delta H value, which is indicative of how thermodynamically favorable the reaction is. Then I've got this bump right here. I've got this this barrier, and this barrier is the activation barrier, and I need enough activation energy to get up over this barrier. And now we're talking about chemical kinetics, and that goes to this plot on the right-hand side. And this is an Arrhenius plot, which is some reaction, the natural log of some reaction parameter or some parameter that sort of monitors the progress of the product formation as a function of 1 over temperature. And the slope of this line is proportional to the activation energy of this barrier. Now, this is all thermodynamics, and this is all chemical kinetics. But when we talk about plasma ALD, plasmas are energetic gases that can actually access chemical pathways that are not accessible thermally. So this opens up a whole new class of ALD materials when I use plasma ALD in order to make a material. And so because plasmas have a lot of this internal energy associated with them, that we can actually make products that wouldn't necessarily be accessible thermally with mere thermal ALD. So let's take a look at real quickly what a plasma is. And a plasma is really just generated by, it's a gas, it's generated by an electrical discharge, and typically are sustained by these alternating fields. These fields excite the ions, positive ions one way and the electrons the other way, and then I flip the field, and then I smash them back into one another, and I flip the field, and I smash them back into one another again. And so I just constantly keep these things moving around, and it's the collisions that sort of heat the gas and then maintain the plasma. So plasma is actually a whole area of physics in and of itself. The plasmas are different in terms of the relative concentrations of electrons, ions, and neutrals. There's primarily two different classes of plasmas, and that's the direct plasma and the remote plasma. And the direct plasma is when your sample is physically inside the glowing area or arena of the plasma. Where a remote plasma is when my sample is a little bit downstream, and I allow the radicals and the ions from the plasma move downstream and then react on my sample. So remote plasmas are typically lower in pressure due to increasing the mean free path, so that I can deliver or transport some of these radicals and neutrals down to my surface. So these plasmas are reactive, and they provide the surface energy in the form of radicals and ions to produce these chemistries. The typical problem with plasmas is that there's a certain finite lifetime to them, and when I'm trying to get a plasma to go down a trench to do plasma ALD, I'm now in the molecular flow regime in a trench, and so we might just neutralize those ions and those radicals that are used to perform chemistry. So plasma chemistry doesn't work very well, or only a finite, doesn't work very well down trenches. So depending on the aspect ratio and the overall diameter of the trench with respect to the mean free path of the plasma itself. So there's a problem with plasmas. Plasmas are typically oxygen plasmas, nitrogen plasmas, hydrogen plasmas, ozone, ammonia. Those are plasmas. Now, ozone is not necessarily a plasma. It gets generated in a plasma, and it's just an oxygen radical source that can be transported many, many feet. So ozone is a very good source to make low temperature oxides. Now, as I mentioned, plasma species have finite lifetimes, and because the components are only really alive, say, in the plasma itself, they're going to have finite lifetimes outside the plasma. And so this is important for plasma delivery. So as I said, in remote plasma, they usually run them at lower pressures so that the mean free path is longer, and I can deliver these radicals to the surface. Hydrogen is my one example here, is that hydrogen radicals, or atomic hydrogen, will recombine on the walls of a container to make H2. So I have a surface, I come in with hydrogen radicals, and hydrogen radicals will just decorate and coat the surface. And when another hydrogen radical comes down and hits the surface, it will actually react with that hydrogen on the surface and then desorb and form H2. So if you're using hydrogen radicals, they have they can recombine on the walls of your surface or the walls of your trench, and that decay is exponential as you go down a trench or down the walls of a reactor. And the rate at which that recombination takes place is usually much faster than metals, than insulators, and that's also why you typically run remote plasmas at lower pressures. And so ozone lasts a very long time. It seems that nitrogen is a very short-lived radical. Next would be hydrogen, and then oxygen. So N2 plasmas are very difficult to use remotely because they just don't. The nitrogen radicals don't live very long, just because of that triple bond between each of the nitrogen atoms. Now let's look at oxygen plasma as an example. And so we have O2 plasma here to make metal oxide, some sort of metal oxide. So I come down here onto a surface with a metal organometallic precursor. It will probably sit and be in a physisorption state on the surface. Now, it won't chemically bond with the surface. It'll be in a fizzy-sorbed state. I'll purge it after I've reached surface saturation, and I'm left with this, maybe this organometallic surface. And then when I come down with the oxygen radicals, it'll strip away the organometallic or the hydrogen that's in that molecule and make the oxide. Once I do that, I purge that away, and then this surface is ready again for my organometallic precursor to come down in. And again, it might sit in a fizzy-sorbed well. It actually might chemisorb to the surface. But the idea being is I do that, and then one of my exposures is an oxygen radical exposure, oxygen plasma exposure, and then I oxidize the surface, and I, at the same time, remove any of the byproducts, probably carbon dioxide and water from the surface. Another example would be ammonia plasma. Here we can use this to make aluminum nitride at 150 degrees C. So here I have a surface here, and I've got this NH on the surface, this nitrogen hydrogen, that's my reactive handle. I come in with trimethyl aluminum. It'll react with that NH bond and make methane and hydrogen gas. And so now I've got this methyl terminated aluminum surface right here. I'll take ammonia plasma and expose that. That ammonia plasma will react away those methylated groups on the aluminum and make a nitrogen aluminum bond. And then once that's done, I'll produce products of probably hydrogen and methane. Once that's reached surface saturation, I've got this aluminum nitride surface, and this surface is terminated by NH bonds that are going to then re-react with the trimethyl aluminum as I come down to my A step. So these are two plasma examples, and that's the plasma ALD section. And I'd like to just quickly go into 2, 3, and 1 component ALD materials. And I didn't name it 1, 2, and 3. I named it 2, 3, and 1 component materials. 2 component materials, like oxides and nitrides, they make sense because we've got these half reactions. And half reactions, AB can give us our metal nitride, metal oxide, metal nitride, metal nitride. So it just sort of makes sense with half reactions and 2 component materials. And that's all I'm going to say about that. 3 component materials is a natural extension of the half reaction, but we're going to do third reactions. So instead of doing AB, 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 we're going to do ABC, ABC, ABC. Now these reactions are a little more tricky. They're a little more involved because it's 3 precursors. And kind of limitations, ALD has some limitations in making those types of compounds. Now 1 component materials, namely depositing elements on a surface with ALD half reactions, follow different rules of chemistry. So I'm going to go through 4 examples of those different kinds of chemistries, how to put down single element materials. And that's kind of my favorite part because it really is kind of unique. So when we do 1 component materials, one of those AB cycles is going to be a reducing step to reduce the element oxidation state down to the single element 0 oxidation state. So let's take a quick look at 3 component materials. This is a quick cartoon of ternary materials. As I mentioned, we have an A reaction, a purge step, a B reaction, a purge step, and a C reaction, and a purge step. And then we can repeat this process. But we're really sort of at the mercy of the surface chemistry in terms of controlling the stoichiometry. Now, I know that I would love to be able to control 3 component stoichiometry, but I'm really sort of at the mercy of the surface chemistry to determine how many of these sites I'm filling with the B reaction and how many are on the C reaction. So these are somewhat limited. These materials can be grown at a much lower temperature than their ceramic counterparts, but their ceramic counterparts are much higher quality films. The growth rates for these are much lower per cycle typically, and what the challenge of this is to find the overlapping ALD window for each of these half cycles, or third cycles, excuse me. So we need to have a temperature where all 3 of those chemistries happen efficiently enough that give us the right stoichiometry for this to work. And so that can be a challenge. And so some might work at higher temperatures, some might work at lower temperatures. And so finding that common overlapping temperature ALD window can be a little tricky for these materials. So 3-component materials could be your barium titanate, strontium titanate, what do we have? Gallium indium phosphide, copper gallium sulfide, these kinds of materials. And I'd like to point out Lori Ninisto from the University of Helsinki University of Technology. He did a lot of the groundbreaking work on these 3-component materials. So, so I just wanted to give a shout out to him. Now let's talk about single element materials. So single element materials was once not thought possible because AB cycles in ALD would put down a metal oxide or metal nitride. So how do you put down a single element using ALD chemistry? Now the trick is to reduce the surface species to produce some sort of oxidized gas phase byproduct and reduce that element on the surface down to its zero oxidation state. So there's different possible avenues with this single element ALD, and I'm going to go over 4 of them. And we'll notice that always one of the half reactions is a reducing step to deposit the element onto the surface. So the first one I'd like to talk about is using a sacrificial reactant to deposit the single element. And this is used to deposit tungsten, molybdenum, and tantalum metals. It uses disilane gas as the reductant gas, and it works exclusively with these metal fluorides, tungsten hexafluoride, moly hexafluoride, so on and so forth. So here's how this chemistry works. Is I have a surface and I come down with disilane, and it'll form this, maybe a multi-layer. It'll form, there might probably be some fluorine on the surface. I'll give me that as an assumption. And I'll make this fluorosilane species on the surface. So this is going to be the reducing surface, but I put that reducing surface down first. And it's in terms of this silane, this fluorodisilane moiety on the surface. Now I have this surface, and I come in with my tungsten hexafluoride or my molybdenum hexafluoride, and when I react that surface, these metal fluorides, the fluorine from the metal will react with all this silane on the surface to produce this trifluorosilane gas phase species with sleeves. And at the same time, it actually reduces the metal from the plus oxidation state down to the 0th oxidation state or the +1 metal oxidation state, and leaves behind a metal fluoride surface. Now I have this metal fluoride surface, then I can expose it again to disilane, creating this fluorosilated species over here. And then once I have this fluorosilated species, I come in with the metal hexafluoride, and then this fluorosilated species actually reduces the metal fluoride gas down to the metal oxidation state of 0 or 1, again, leaving behind the fluorinated metal fluoride surface as a reactive handle for this disilane chemistry. Now, the single thing to point out about this chemistry is that the layer thickness of this disilane surface is going to determine the growth per cycle of how much of this tungsten goes down. So at certain temperatures, at higher temperatures, we can get silicon-silicon bond insertion and actually grow a multi-layer of this fluorosilated species on the surface. And so if I have a thick fluorosilated species, then I come in with my metal hexafluoride, I will put down more tungsten metal onto the surface. So the surface growth per cycle is controlled by how much of this fluorosilated species is on the surface. But with that being said, it's pretty remarkable that you can deposit tungsten, which is a great metal to deposit, an important metal in the semiconductor industry, using ALD, and you can actually do this at a reasonably low temperature, like 125 degrees C. You can deposit tungsten metal. So that's very exciting. So this is one method on how to deposit a single element, and that's using disilane as a reducing gas, making a multi-fluorosilated species. But mind you that it only works for 3 metals on the periodic table. Now let's go to another way to deposit a single element, and that is the combustion. the combustion reaction of organometallic precursors with oxygen. And this is really my favorite way of depositing because I just have so much interest and respect for the chemistry. So we'll talk through it. So I have a surface right here, and I have some oxygen on the surface that's in a fizzy-sorbed state. So mind you, if it's a fizzy-sorbed state, it has a very low temperature window. And when I bring down an organometallic precursor, it'll react with this fizzy-sorbed oxygen and combust. It'll actually make carbon dioxide and water and bond with the surface. And so now I've got this, it'll bond with part of the molecule onto the surface. So now I've got this organometallic surface here that's inert, and I guess I should back up and say that we use this to deposit platinum and ruthenium metals. Now remember, these metals don't necessarily form good oxides. So we're able to keep that oxygen on the surface without making an oxide bond. It just sort of sits on the surface. I should have mentioned that earlier. But now that I've got this I've got this metal down here that is still in the oxidation state and it still has some sort of organic precursor on it. As I expose that metal precursor, organometallic precursor to oxygen, I actually react away all of that organic part of that precursor. I reduce that molecule down to its base metal, and I burn away that carbon and oxygen in terms of CO2 and water. But what's important to know is that this oxygen exposure will leave fizzy-sorbed oxygen on the surface. So here's some fizzy-sorbed oxygen on the surface, and that is a requirement in order for me to run the A cycle to bring in the organometallic precursor to react with that fizzy-sorbed oxygen. And so if my reaction is too hot, the oxygen will not stay on the surface, and my reaction will shut down. So if the temperature is not warm enough, I won't actually undergo this oxidation step. So these particular chemistries have very smaller ALD windows, and it's primarily due because we're relying on this fizzy-sorbed oxygen on the surface to actually drive the AB cycles. So I like that chemistry. It's very interesting, and you can put down platinum metal with it, which is remarkable. So the third way is really just a thermal reduction of ALD. And so what I do is I make the metal oxide. I can use this organometallic precursor with water or ozone. I can use nickel ACAC or copper ACAC or nickel CP. React that with water and oxygen, and I just make the metal oxide over here. So I make the metal oxide, and I take that and I stick that metal oxide in a furnace with hydrogen, or I can use atomic hydrogen at a lower temperature, and I reduce all of that metal oxide down to the base metal. So it's not cheating in a way, but it is a way to make metals with ALD, but you make the oxide first, and then they undergo reduction to the base metal. But what's interesting is that actually you can grow about 250 nanometers of material and then convert all that metal oxide down to metal. So you don't have to do this one step at a time. You can grow the full oxide and then reduce it down to the base metal. So it's been used to deposit, like nickel and copper, and also platinum metal. It's been done this way as well. All right, so the last way we can do this is hydrogen plasmas. And so here we come down with an organometallic precursor, and then we have this organometallic precursor probably in a fizzy-sorbed state, and then we expose to radicals, hydrogen radicals, and radicals will just strip away all of that organometallic precursor, turning it into methane or water or what have you, whatever the organic is, and then I'm left with this very naked and very vulnerable metal surface, and this metal surface will enable more of this organometallic to fizzy-absorb down onto it. Again, I expose it to hydrogen, and I strip away all the organometallic material, which reduces the metal down to the base metal. Now, this is a difficult way to make these single elements, but I just thought that because of the attenuation problem with delivering hydrogen radicals, and that this surface is so reactive to any oxygen in the reactor that this might oxidize very quickly. So you might end up making the metal oxide, not necessarily the base metal that you want. So those are 4 different methods on how to make single elements with ALD. And the last thing I want to talk about is molecular layering ALD. And I just have a single slide on this. And so MLD, which is also very exciting because it's this combination of inorganic chemistry and organic chemistry. So the way this works is that instead of using water as my oxidant source for ALD, I'm going to use an organic molecule. So one example is this ethylene glycol. You'll notice that we have 2 OHs on either end of this molecule. And what I have circled here in red is an H. I have 2 H's and an O. So this molecule can essentially react like water, but it has these carbon chains between it. So here's a methyl-terminated surface of aluminum methyl bonds. I come in with ethylene glycol. Now one of these OHs is going to react with that methyl group and make an oxygen aluminum bond. And then this organic moiety will actually stick onto the surface, producing an OH surface. Then I can have this OH surface in the B reaction, react that with trimethyl aluminum, and those OHs on the surface will then react with the methyl groups, again creating an oxygen aluminum bond, and then recreating this methyl surface. So that's the basic part of this. You can see how exciting this is because it doesn't have to be ethylene glycol. It can be any organic molecule that has 2 functional groups on it. It can be a ring structure. It can have 3 organic groups on it. So the combinations of what chemistry you do for your inorganic part and your organic part is basically endless. But there's a couple problems with this MLD. One, you can see that I have 2 OHs on this group. So there's nothing to stop this molecule from coming down in both OHs, reacting with those methyl aluminum bonds, and then the surface would terminate, like it wouldn't react anymore. The surface reaction would shut off. So that's no good. So it's probably better to build molecules, organic molecules, that have these things a little further away. These bonds are also can be sensitive to oxygen, and as you grow these films, they kind of become a little more disordered, and they start to tip over, and they don't really grow in this bond just because of the degrees of freedom of rotation of those organic molecules have. Also, these films are low density and they're spongy, and so I can get precursor to sort of absorb into this sponge of the organic network, and then I can get sort of this CVD film to grow. So this particular area has its challenges, but I still find it very exciting because it's a combination of both organic and inorganic chemistry. So that ends the atomic layer deposition section, at least the chemical part of it. And so we're here, and I'm going to take a 10-minute break, and I'd be interested in asking questions. So folks can take a deep breath, go use the facility, and I'll go talk to my assistant, and we'll see about answering some questions. So we'll start again in 10 minutes from now. All right, thank you. Well, it's going to answer some questions. Yeah, let me look at some questions, and let me get back to you in about 5 minutes. I'll put myself on mute. We have a question from Natalia, and she's asking what the difference between ALD and sputtering is. And so I think that maybe that question hopefully has already been answered. That sputtering is really sort of a line of sight technique. It involves the thickness control. It doesn't have a sense of thickness control that ALD does, and it can't code high aspect ratios. And typically sputtering is that you're removing a film from a target or from some source and then spraying it essentially onto your substrate. So that's the difference between ALD and sputtering. I'm sure other people could answer that question as well. And then Rick Deb here, he said, what was the approximation also hold for stainless steel, whose molecular weight we cannot know since it's an alloy? Is 10 to 15 still a good approximation? Yes, I think it's a very good approximation. I mean, I think that I'm not sure what stainless steel you're working with, but steel is like, is it 4 irons and 1 carbon atom? I think that's what stainless steel is, but you put in some molybdenum and some other things in there. So yeah, that's still a very good approximation. As I showed, as density changes, the value still hovers around 10 to the 15. We have another question here. How does, sorry, hold on. I lost a question in there. How to decrease the sticking coefficient in CVD process for a given deposition material, for example, silicon nitride? Well, your sticking coefficient is going to be defined by your precursor molecule. So if your precursor, the way that precursor interacts with the surface will have a varying effect on its particular reactive sticking coefficient. So some precursors stick better than others, and if you want to coat a trench with silicon nitride, you want your precursor to not stick very well. And so if you look in the literature, I'm sure there are some a list of precursors for silicon nitride at higher temperature CVD that have lower sticking coefficients. So hope that answers that question. This is a question from Miriam. What are the substrate examples in slide 29 and 30? I forget what those slides are, but you have another question. So how do I define the optimum ALD window given known initial conditions on slide 35? So I think that's the ALD window slide. You don't define the optimum ALD window, you just sort of find it. And where you find it is as I change temperature and the growth per cycle stays the same. Now, if you feel like you're outside the ALD window, you'll see it dramatically. You'll see a dramatic increase or decrease in your growth per cycle. So, but again, there's that soft saturation that I talked about. So you might see some variation in your growth per cycle just as a function of temperature. So, you know, there could be just some small variation in the thickness per cycle within your ALD window, but when you're outside your ALD window, you'll definitely know that you're not doing ALD chemistry. Okay. Another question is, how would one widen the growth per cycle windows? Basically, which are the most important factors influencing it? Well, I'm going to talk about that momentarily. So growth per cycle is, I'm guessing you want to get the highest growth per cycle. And so sometimes, in one example, when you use a very large chemical precursor, some large organometallic molecule that just takes up a lot of real estate on a surface, you will inherently have a lower growth per cycle. So how to speed up that growth per cycle would probably be trying to change to a different kind of chemical precursor. Maybe something that's maybe more reactive, or maybe a smaller molecule. I think we're kind of like locked into a growth per cycle, but that's a good question, how to change that. So we have a question here. Since many schematic examples throughout several slides don't specify the substrate material, does it mean that the reactions occur incidentally regardless of the nature of the substrate? I think that question is sort of maybe approaching the growth versus nucleation question. So I had some sort of random substrate, but I put these reactive handles, these hydroxyl groups or these NH groups on the surface, which sort of allow the cyclic nature of the ALD chemistry. When we talk about nucleation, that's a very different substrate, a very different surface. So that takes different chemistries to actually get the surface to nucleate before we're in the growth ALD regime. So I hope that answers that question. And then we have a question here about TiO2. Is it possible to control the crystallinity toward the rutile phase? So that's an excellent question. I'm not an expert in TiO2, but I know that it goes down polycrystalline, and I'm not sure if it's in the rutile phase or not. Is it possible maybe to try to anneal the film at a higher temperature to see if you can't drive it into a rutile phase? But still, it would be polycrystalline if it was in a rutile phase. So that might not be what you want. And Joe's asked, what are the typical stress states, tensile versus compression, observed for ALD in compounds like aluminum oxide or titanium oxide? Can stress be controlled? So stress can be controlled in CVD, but you know, that's an excellent question. I don't have good familiarity with the compressive versus the tensile stresses of ALD films. That's a very good question, and I don't think I've come across any literature on it of what those stresses are. But that's a good question. I wish I knew more about that, so maybe I'll look into that. And then we have a question: could you recommend some service companies that are specialized in ALD deposition, especially iron oxide or nickel? I'm guessing that's nickel oxide. You know, I don't know. I'm not sure offhand if I know of any companies that do that. I would just poke around the internet and see what you can't find. Iron oxide shouldn't be too complicated. It should have a low growth rate. Nickel metal, we kind of went through that as an example, but yeah, I don't think I can recommend something. I'm not sure. I'm not sure. So our break is a little bit past due, so we're going to get started again. Thank you for all your questions. I hope that helped. And so we're now going to move on to chemical precursors. So if you're a chemist, you might really like this section. If you're not a chemist, you might not like this section. So the two things that I'm going to talk about are the chemical property, the precursor properties, and the delivery techniques, because we talked about that precursors can be solid, liquids, and gases. And then I'm going to talk about the necessary precursor quantities. And that's really going to go back into the reactive sticking coefficient, the flux, the pressures, the flows. And so we're going to drill down into those details. So we know that ALD is a gas-phase process, but what drives the ALD process is the energy that's in the reactant. So if I can build a reactant that's very energetic, that's also probably very toxic and very pyrophoric, it's probably an excellent chemical precursor for ALD because it drives the temperature down. So we really want to build all the chemical energy into the precursor molecules so that we can perform the ALD chemistry on the surface. So that's sort of why it's a unique area, a very growing area of ALD research is the chemical precursors. So let's take a look. So you know the film properties, the impurities, the compositions are all a result of what precursor you choose. And precursors can be gases, liquids, solids, or plasmas. So that's neat that we're using all four states of matter just for chemical precursors in ALD. And I'm not sure that any other deposition technique uses possibly all different forms of matter. So we know that the precursor must be volatile to get up into the gas phase, and it also has to be thermally stable to get the vapor pressure up if we need to, just to get it into the gas phase, into the reactor, and then to react on our surface, on our substrate. We need it to reach surface saturation and not multi-layer absorption. So that ALD precursor, we don't want it to react with itself at higher temperatures. So maybe that compound is stable at low temperatures, but as soon as it hits a hot substrate, it has a surface reaction that then makes it react with itself. And so we can't have that, or we don't get that surface limiting behavior that we know and love about the ALD chemistry. The surface reaction needs to be thermodynamically favorable. It has to have a large delta G. It has to be thermodynamically spontaneous. And the more, as I mentioned, the more reactive the chemical precursor, the lower the temperature we need in order to run the reaction. So if we want to coat polymers or temperature-sensitive materials, we probably want to use the most energetic, toxic, and pyrophoric ALD chemical so that we can drive that chemistry at the lower temperature to get the ALD to happen on these low-temperature substrates. And then, as I mentioned in the questions, is that the larger the molecular precursor, the lower the ALD growth rate. And I said rate there, I apologize, it should be growth per cycle. And that means that the real estate that this molecule takes up on the surface is going to limit the number of molecules on the surface at surface saturation. So when I bring this big organometallic molecule down, it sits on the surface, and then I react away all of that organic part and leave the central atom behind, my growth rates go down substantially. So you might see the bigger the precursor, the smaller the growth per cycle. So let's take a look at some typical precursors. We have 4 classes of precursors. We can have metal halides, we can have metal alkyls, metal alkoxides, and we can have organometallic compounds. So metal halides, I talked about the tungsten hexafluoride that we use for tungsten ALD. We have titanium tetrachloride that we can use for titanium oxide. We have aluminum trichloride. Aluminum trichloride is actually a solid. And we also have other iodides and chlorides and bromides. So this is sort of like the metal halide camp of ALD precursors. The next section would be metal alkyls, and this is where we actually have a metal and a carbon-containing bond. And so we have there on the short list, we have the trimethyl aluminum right there is the first one, and that's what we use to deposit aluminum oxide. We have diethyl zinc right below it, and that's used to deposit zinc oxide. We also have some other more exotic. We have cadmium-based metal alkyls and mercury-based metal alkyls. I don't recommend doing either one of those 2 ALD chemistries, but know that they exist. Then we have these metal alkoxides, and this is a metal bonded to an oxygen that's bonded to a carbon. So that's a metal alkoxide bond. We have aluminum ethoxy. We have titanium tetroxide. We have niobium and tantalum compounds. And mind you, these are just very small select examples of these different kinds of chemical precursors. All these precursors can come in gases, liquids, or solids. And as I've mentioned, that ALD precursors are typically toxic and pyrophoric. So care has to be taken when you handle them and also when you clean out your reactors. So the other class of compounds is going to be the organometallic compounds. And here's a couple cartoons of what these compounds look like. I have a scale bar in there for reference. We have these beta diketonates. We have these cyclopentadienyls. We have this one particular molecule, this tetrakiss dimethylamidose, and then I'll probably butcher this up, but this is the dialkyl acetamidase. So I'm talking too long, but that's the 4th one in red there. So the beta diketonates, we have 2 of those. Mind you, there's all sorts of varieties and flavors of these, but the ones you should be familiar with are the acetyl acetonate, and that's designated AC. And so you might see like copper AC 2. So the AC is that molecule that I've shown there. You can see that there's a central metal atom there. And so you'll just see it in the literature as copper AC. And that's what the molecule looks like. Notice that it's a relatively large molecule. An even larger molecule in the beta diketonates is this 2266 tetramethyl 3,5 heptene dienate. And that's also described in the literature as demarcated as THUD, THD. So you might see a molecule that has a metal atom with THUD or THD. And what they're referring to is this very large, very exotic atom right here. This molecule, again, it's a large molecule, has a lot of real estate, is typically used to put down more exotic metal atoms on the periodic table. The third are these cyclopentadienyls. We have CP, cyclopentadienyl. It's a 5-membered carbon ring with 2 double bonds. And then we've got this methyl cyclopentadienyl as well. The most interesting precursor from this is the platinum precursor, which is trimethyl cyclopentadienyl platinum. So you have a platinum atom, you have 3 methyls that stick down as a tripod, and then you've got this CP ring that sits on top. And that's the precursor that's used for platinum ALD. Then you've got your tetrakiss dimethylamidose. These can come in different flavors like zirconia or hafnia, and those are still primarily the precursors of choice for those particular metals to make a hafnium oxide or a zirconium oxide. And then this one here, the one I can't necessarily pronounce very well, I'm not too familiar with that compound. I know that it exists, and I don't necessarily have any examples of that particular compound and what ALD that it's used for. Now, I mentioned that these can come in, precursors can be gases, liquids, and solids. Ideally, they're gases. Second idea would be that they're high vapor pressure liquids. And then what you don't want is necessarily work with solid precursors. But these organometallic precursors are typically solids, so you need to heat them up in order to get the vapor pressure up. But when we talk about liquids, we know that we can deliver liquids in a few different ways. So if the vapor, we need to increase the vapor pressure of the precursor in order to get enough of that vapor up into the chemical reactor to coat our parts. So some liquids, like I mentioned, water or trimethyl aluminum, have high enough vapor pressures where we can just sit there and draw off the vapor. Vapor pressure of water was like 20 torr, I think. The vapor pressure of TMA was like 10 torr. That's plenty of vapor to just draw off the top of that, because as soon as we pull that off, it's going to give us a constant draw of 10 torr, 20 torr of vapor. Now, other liquids, we can actually heat the precursor, so we might need to wrap them up to get them into a liquid phase and then get the gas to get the vapor pressure up. We can do that with liquids, just heat them up and we get substantial vapor pressure. The other methods are really to use a bubbler, and here we'd have like a nitrogen straw into your liquid, and what I would do is I would actually bubble nitrogen through the vapor, or through the liquid, and it would actually sort of atomize or bring vapor to the surface, and then I can draw that vapor out into my reactor. But these are tricky ways to do it. Just because if you've ever worked with it, then you can bump this by accident and you get liquid precursor into your chamber, which then can cause CVD to occur. So these are tricky. They're doable, but you can do one by just sweeping N2 liquid through the vapor itself and sort of bubbling it up and increasing the vapor pressure that way. Other methods is that you can heat this ampule, and then you can pre-pressurize it with nitrogen up to maybe, I don't know, 20 psi, and then let it go, and then you'll get this rush of vapor that comes out of the precursor container and then into your reactor. So it's sort of like pre-pressurize it and then burp out the precursor. And so precursor delivery is still a very important area of ALD reactor design, just because of myriad possibilities of ALD precursors. We really need to be able to deliver them successfully and without particle generation. Now, solids are a different beast, and the solids obviously have much lower vapor pressure. And so one of the ways you can deliver them is you have a large oven with all these little trays of your solid, and that's just to get the sheer quantity of vapor, or the sheer, it's a low vapor pressure, but the sheer number of atoms into the vapor. You'd have all these little trays where you'd heat it, you'd attach this furnace essentially to your reactor, and then that would be your precursor source. But if you're heating this, you have to make sure that all of your lines from your furnace or from your solid precursor are heated to a little bit slightly higher temperature than the furnace itself, because you don't want any of these solids to condense in your lines, because then you'll have particle problems, or you'll cause CVD to happen in your precursor delivery lines. So then you'll have to get one of your grad students or some subordinate to clean it out for you, and you don't want to do that. The other thing that can happen with solids is that you can form a skin on top of the solid. So you heat it, and then sometimes the vapor pressure just starts to turn off, and it's because you've sort of made this skin on top of the solid, and so sometimes you have to chip away at it to get it to go again, and to reproduce and start producing precursor vapor. So solids are pretty tricky to deliver. They can be delivered, but they're tricky, and it depends on the particular compound or material you're trying to grow, depending on how much trouble you're going to have doing that. Now, many solid precursors, like those wonderful organometallic precursors, will actually decompose before you heat them up, or before you heat them up to liquefied temperatures. So I can't really just sort of take that precursor and then heat it to the liquid phase and then draw the vapor off, because the chemical precursor is going to decompose. So we usually use like thermogravimetric analysis to determine the optimum temperature for delivery. So here's an example of a TGA on the right-hand side of your lower right-hand side of your screen. So I put a solid into it, and then as I start to see the weight loss with the TGA, I start to see that it decomposes if I heat it to a high enough temperature. And so I don't want to work in that temperature regime with my chemical precursor. I want to be somewhere before this first cliff right here. I want to sort of run my furnace or heat my chemical precursor somewhere there so I can have a safe delivery of the precursor, but not necessarily decompose it inside my inside the lines of my reactor. Now, when we talk about solid precursors, it was actually one of the first chemistries to be done using solid precursors. And so I'd like to reference the ASM, or the microchemistry F120 reactor. And so it was the first production scale reactor. I presume it was designed in the 70s. And it was designed to actually harbor solid precursors with low vapor pressures for whatever application they had. So this is sort of a grand design of the precursor flow. And essentially, this the precursor compartment where you can put these wafers in here. And you have this exotic gas valving system where you actually use these little gas windows because we've had to run this at a very high temperature. None of the valves at the time, there weren't any valves that existed that could actually be heated at a high temperature and still operate properly. So I won't go into much detail out of this, but you have this sort of giant glass head that had these drillings into it where you can put your, you sandwich your precursors into that, and then you use these exotic gases and these little gas windows I've shown here to keep the precursors isolated while the other precursor was actually being delivered. So just moving valves around and having flows of gas in certain directions could isolate precursors or actually enable them to get delivered to the precursor or to the sample chamber. But so we needed this gas window to separate the A pulses or the A half reactions from the B reactions. So this worked very well. So it was sort of ironic that the first precursor they tried was designed for solid precursors. So the next way to deliver precursors is through pneumatic valving. And so pneumatic solenoid valves can use for reactant injection. And so modern valves can actually withstand high heat and are very, very fast. So that was sort of driven by the ALD community to have these precursor valves that I can heat to high temperatures and that can respond very quickly. So I want to point this particular kind of delivery system out in a little more detail. Here we have, this is from a design by Jeff Elam. We can see here we have a water precursor and we have our flow tube. So this is how this, and we have a nitrogen source. So nitrogen comes through here and typically just flows through the ALD reactor tube. And back here in the reactor delivery manifold, I've got two solenoid valves, A and B. And I've got a mechanical pump attached to the B. And I've got this needle valve right here. So when I'm going to do when I'm not going to do a pulse, I have this mechanical pump turned on. This valve is open. The A valve is closed. And a little bit of this nitrogen flow goes backwards through the needle valve and then down to the mechanical pump. So I create this gas window right here to isolate the water precursor from the reactor. And also, if this valve is a little bit leaky, some of that water will just get sucked down to the pump. Then when I want to do an actual water pulse, this valve gets turned off. This valve gets turned on. And so now all I've had was nitrogen in this part of the delivery system. Water will get sucked in through here into the chamber and then down to perform ALD. When I'm done with the water, I will turn off this valve A to isolate the water, but then I turn on valve B. So any of this water that was trapped in here from the water pulse naturally will get sucked down and away from the pump. So it really adds a more efficient mechanism to make your pulses shorter by having the second channel that sort of protects the water source from leaking, but also sucks out any of the water that might be left in here to make that water pulse faster in time. And so if you're going to build an ALD reactor, I recommend that you use this design for your valving system. Now, the last thing I want to mention is shower head delivery. I just mentioned this because it's used in the semiconductor industry to coat 12-inch wafers. So you've got to have your ALD precursor delivered across 12-inch wafers. And since time is money, we really want to get that distributed very quickly to decrease the pulse and purging times as we're doing these ALD chemistries on large surfaces. And this is just used in the production production reactors. And since the semiconductor industry is moved to these 300 millimeter wafers, these 12-inch wafers, we want that, and time is money, we want to make sure that our pulses and our purging times for ALD deposition processes are as fast as possible. So that ends the section on just precursors and the delivery. But now let's talk about the actual necessary quantities that we need that we need to perform ALD chemistry. So we talked about flux here in the cartoon, and we talked about the number of surface sites per centimeter squared. Now I have an equation for flux right here. I have a concentration of surface sites, which is 10 to the 15 per centimeter squared. So if I divide the number of the concentration of surface sites by the flux, I'll get the amount of time that it takes to coat that particular surface at that pressure. And so now we're back to that's the time it takes. And if I take that time and multiply it by a certain pressure, then I get the exposure that I need in order to coat a given substrate. Now, if you want to think about exposure, it's just exposure. If I have a flow tube, exposure is just this packet of reactive molecules. It's enough just to go through the reactor and coat all those surfaces or saturate the ALD half reaction. Now, this just is not including the reactive sticking coefficient. So if I include the reactive sticking coefficient, which I have to because it's an ALD chemical process, then that indicates that I have to increase the exposure necessary to run those surface reactions to completion. So here's a cartoon of a reactor. I've got this liquid over here. I've got this nitrogen flow that's constantly flowing through my reactor, typically to keep the reactor at about a torr. Then I've got my surface right there. Reactants are coming down and products are being generated. So I need to know the reactive sticking coefficient of my process. Then I need to calculate the exact reactive chemical exposure I need in order to have that reaction run to completion. Then from there, I can calculate the flux of molecules that are actually hitting the surface. And then but in order to determine that flux, I need to know what the partial pressure is of the reactant in the flow. And I need to know the area of the reactor and the time required for the chemical exposure. So I really have to start with the chemical precursor and how much vapor am I getting into the flow. Once I know that, then I'll know what the flux of my chemical precursor is to the surface. And knowing that, I can know what the chemical exposure is that I need by knowing the reactive sticking coefficient. So that's the things that you have to take into consideration when you're determining how much chemical reactor or how much time that you need to expose a surface to a certain chemical. And typically, we just run our ALD reactors in excess, and we don't really necessarily worry about these particular kinds of details. But when we get to coating high aspect ratios, which require larger chemical exposures for conformal deposition, that's in a different regime entirely, again, because we are in a molecular flow regime in a trench and not in a viscous flow regime, as I've shown here on this slide here. So speaking of high aspect ratios, let's talk about substrates and surfaces. And I want to go over high aspect ratio structures in a little bit more detail than maybe you'd like. I'll go over particles, and then I have a slide on roll-to-roll chemistry. So let's go over that, and then I think we'll have a break after that. I'm not sure. Maybe it's after that. So let's talk about high aspect ratios. Let's just slide motivates the subject. And so high aspect ratios can be pores in a membrane. They can be trenches that have been etched in a semiconductor process. They can be tortured paths like maybe a zeolite or something that's very, very small. Or it could be a MEMS device that has a that has this overlaid feature or this tortured path to get into like a wheel hub. So coding these high aspect ratios is actually very important, and it really enables their functionality. We can close down these pore sizes for unique membrane applications if we want to reject large molecules and let small molecules pass. ALD gives us the potential to do that. If we want to change the surface type, if we want to make a hydrophobic surface or a hydrophilic surface for microfluidic applications, we can do that with coding these high aspect ratios with ALD. Also in 3D electronics, I mean, as we've typically electronics are built, there's an active area of a device, and then we have all these vias that get down to the active area. But now in these new FinFET applications and 3D NAND structures, we're really building electronic structures in 3 dimensions. And so in building that, we have to do a very good job at isolating one 3D component from another 3D component from another 3D component. So coding high aspect ratios for trench isolation and better performance in 3D electronics is a really important area of research for these days. Now, as I mentioned, that the flow of molecules is different inside a trench than it is in a flow reactor. So we really need to increase the pulse and purge times to accommodate that molecular flow that's inside these trenches. And that's what we're going to drill down into next. So trenches are typically defined by their aspect ratio. An aspect ratio is given as the ratio of L over D, which would be the length of that, the depth of your trench divided by the width of your trench, or the diameter of your trench. And so aspect ratios, they can define a pore as well as a trench-like structure. So one interesting experiment that was done was performed on this nanoporous anodic aluminum membrane. And this is like a piece of aluminum foil, and you put the right particular voltage on it and use this electrochemical process, and you can actually etch pores right through your membrane. And so in this picture here on the right shows the pores. There's the side view. You can show that they're 40 nanometer pores. They're 40 nanometer pores. I mean, they're very, very small. They're 400 angstroms wide. And you can see a top-down approach that they're pretty reasonably in a good array. You can see that they're pretty consistently sized whole pores. They're all about 40 nanometers in width, and then they have aspect ratios of like 2 times 10 to the 3, so 1,000 to 1 ratio. So they're 1,000 deep to 1 wide. So that's actually a very aggressive aspect ratio for any deposition technique. But what we need to do is we need to accommodate the molecular flow of the ALD precursors going down the trench and then the ALD byproduct coming out of the trench in order for a successful conformal deposition of these anodic alumina pores. So that's exactly what was done. The idea was that we were going to do anodic alumina at different times, different exposure times, different pulsing times, and purge times, and on different membranes. And we're going to cut the membrane from corner to corner. And we're going to analyze how much film was deposited at the top versus how much film was deposited at the middle. And so if the middle is thinner than the top, then we know we haven't waited enough time of exposure in order to get the chemicals to go down that. So let's take a cross cut of that. And so here's the data from that. So you can see that here are the pores imaged at the top for 1, 3, 10, and 30 seconds of time for exposure. Here's the middle, and here's the bottom. So notice at 1 second exposure, the middle is not coated as well as the top. At 3 and at 10 seconds, you can still see that the middle has a lower, thinner deposition than the top does. But then when we do exposures of 30 seconds or longer, both pulses and purges, you can see that the holes are about the same size. The open hole at the top is equivalent to the size of the open hole at the middle, and is equivalent to the size of the hole at the bottom. So it looks like that you can coat these anodic alumina structures conformally, you just have to wait 30 seconds for each pulse and for each purge time. So now you've taken cycle times that have been maybe 12 seconds, and cycle times are now on the orders of minutes. But the good news is that you can actually coat these things. And so coating aspect ratios of maybe greater than 10 to the 3, 1,000 to 1, is possible, but at the cost of spending more time allowing your precursors to molecularly flow down the trench or down the pore, and then for your reactant or product molecules to come back out. So this has been more quantified in more detail, and I probably won't go into this in too much detail, but here's the math behind coating an aspect ratio structure, and this would be something that would just be a dead-end pore. It wouldn't go all the way through. It would just be maybe a pour through into a solid. So we have a certain amount of flux here on the surface that we know and love, that we can calculate from our previous learning, but as the reactions occur down the pore, the amount of flux that goes down a pore is decreased by this thing called the Clausing factor. And that is given by this equation here, and it's a function really of the area and the depth down the pore, you know, and so that's your flux will actually change as you go down the length of this pore. So we can calculate the flux or the lack of flux that's going down the pore that's hitting the surface of this pore as we go down the trench. So we're going to need to calculate how much time it takes to actually get all those molecules down this trench. So how do we do that? Well, we take we calculate the time necessary by performing an integral around this delta flux as a function of delta distance. So here's our expression. We integrate both sides, and we multiply pressure on both sides to get exposure. So here's our PT. Here's our T. When we integrate it, we get temperature, and we get this expression here. And I think we've expressed that in terms of the area of the hole. And I won't go into too much math about this, but we have to account for the bottom of the trench. So the exposure is to the sidewalls as well as the bottom. And this is the final expression here, is that the exposure required is this prefactor times 19/4 times A, which is the aspect ratio, times 3/2 times the aspect ratio squared. So it's really interesting in math at any rate that there's this odd 19/4 prefactor in front of this aspect ratio. But that aside, this is how you calculate the total exposure in Langmuir of what it takes to coat that whole structure. So this is a very good publication by Roy Gordon, and if you had any more interest in that, I recommend that you look at that. Here's a cartoon of, I think this was hafnium oxide deposited down this nice trench. I mean, it's a beautiful TEM image, cross-sectional TEM image of the power of the ALD chemistry. So now let's talk about coating particles. So ALD coating of particles. Particles are really used in a lot of many applications, whether we mix them in with epoxy to make it more thermally conducting. And particles actually interact with their surfaces or their surroundings just from the surfaces. But if you see here in this plot on the left, here's the particle surface area as a function of particle diameter. So as we start to make that particle smaller and smaller, the amount of surface area we have per gram of that just starts to skyrocket. And so particles are also weird because they're not flat substrates, they're powders. And so how do we accommodate the surface area increase of powders as well as be able to expose all of those surfaces to ALD chemistry so we can coat those conformally? So there's a couple different methods. Now we know that we can increase the exposure just based on the amount of surface area we have to apply. But how do we get those particles to sort of separate out and conformally coat all of those? Well, what we do is there's one method is to apply a fluidized bed reactor. And so you have a tube here, and you put particles in it, and you flow a carrier gas up this tube that I'm showing you there. And so the pressure of gravity will want to push the particles down, but you've got this gas flow that's pushing the particles up. And under certain conditions, these particles will all separate, and it'll just look like this fluidized bed of particles. And so by doing so, you can have a flow condition where all particles are separated, and then we can expose our particles to a lot of precursor to coat them with ALD. So this is one method, but this method actually uses a lot of chemical precursor because we're constantly flowing it through the fluidized bed every ALD half cycle. Now the second method to coat particles would be use this ALD, a rotary drum. And so here's a cartoon of the rotary drum, where this drum would actually be mounted inside a chamber that holds a static amount of ALD precursor, and so the particles sort of want to fall down to the bottom, but then if I rotate this drum, the particles will get carried up and then fall down to the bottom of the drum again. So if I rotate at the right speed, I can get these particles to sort of separate from one another. And I can also put this in a static reactor and not use so much chemical precursor. I can just sit there and have it bathed or exposed in a chamber of reactant. So in this, I think they ran at 160 RPMs, and it was about a 1/4 inch diameter little basket that they put these particles in. And so over here, they took zirconium oxide particles and they coated them with ALD oxide. And you can see here, not very well, but you can see that these particles have a coating on them. Probably not shown up very well in this image. You can kind of see it. But the particle, kind of the problem with this is that the growth per cycle actually went up to 2 angstroms per cycle. And that's because there's a little bit of CVD going on in here. So this particle bed kind of retained and held on to some of that old chemical precursor. When I brought in the new precursor, then we had a slightly higher growth rate, probably due to some lack of purging time or the lack of being able to flush out that ALD precursor. So we did have some CVD growth into here. And if you want to know more about that, there's this reference here. So the next thing I want to talk about is coating polymers and low temperature ALD. And this is really what's enabled this roll-to-roll processing. And the primary chemistry used for this is aluminum oxide, because aluminum oxide ALD using trimethyl aluminum water can be deposited at very low substrates, low enough that I can deposit it on plastic soda bottles, polymer electronics, flexible display screens, diffusion barriers. I can deposit ALD on paper. I can deposit it on textiles like my clothing, and I can deposit it on mylar membranes to shoot stuff into outer space. So what really has enabled the roll-to-roll process is the low temperature deposition of ALD on polymers. And so here's a summary plot of the properties of low temperature alumina. And you can see the density takes a hit as I go down from like 280 degrees down to 30 degrees C. The growth rate sort of changes a little bit. And so the properties change as I go down to lower temperatures, but still the ability to coat conformally and coat high aspect ratios on low temperature substrates is extremely powerful. So let's take a look at the ALD coating of polymers in a little bit more detail. So this is a quartz crystal microbalance, and this measures the ALD film mass. So this is a quartz crystal microbalance of ALD alumina at 58 degrees, and you can see that the individual steps are actually resolved. Here's where we did a trimethyl aluminum pulse here, and you can see the mass gain. And then we did a water exposure, and then a trimethyl aluminum pulse, and then a water exposure. So we can see that the reaction taking place on the surface of quartz crystal microbalance. Now, if we spin coat on PVC onto this quartz crystal and then run the quartz crystal microbalance on this low temperature ALD chemistry, or if we do it on polymethyl methacrylate, we get two different responses. So notice that on PVC, polyvinyl chloride, we're not really into the growth regime until about maybe about 10, 15 cycles. You can see that there's this little nucleation regime on PVC before we get into the linear growth regime. And that's being observed as a mass change on a quartz crystal microbalance. So that's PVC. But now let's look at it on polymethyl methacrylate. This has a much different kind of signature, and it looks like it takes about 20 cycles to really properly nucleate alumina on PMMA. And look at what's happening here with the mass gain, mass loss, mass gain, mass loss. And so what you're seeing is every trimethyl aluminum pulse, TMA is actually going inside the polymer, and then as I purge, that trimethyl aluminum is getting sucked out of the polymer. So I guess I misspoke when I said PVC actually nucleates pretty much right away. So it nucleates right on the surface, and we're off to the races. Whereas PMMA, you have to undergo about 20 ALD cycles of pushing the precursor into the polymer, sucking it back out, into the polymer, sucking it back out. And by doing that, slowly we start to have a thin film form on in the film, and then we're off to the races. We're in the ALD growth regime for ALD aluminum oxide. So quickly, the model about that is the polymer nucleation model is that this polymer actually can coat on the surface of these particles, or that gets down inside the polymer substructure because it's trying to coat this high aspect ratio. And then if I do enough cycles, I actually start to coat a monolayer of aluminum oxide, and then I just coat aluminum oxide on top of aluminum oxide in the growth regime. So eventually we get the aluminum oxide on that, on polymer. So if you're interested in running low temperature aluminum oxide using TMA and water, this is the table that you want to follow. If you look at 33 degrees versus 177 degrees, look at the amount of pulse times or the purge times. The purge time has gone up by a factor of 20 from, factor of 4 from 177 degrees. And so that you have to wait a much longer time at lower temperature deposition to sweep out all that TMA. The more dramatic effect is actually with water. You have to wait almost 2 minutes, 3 minutes for all that water to get purged out of that polymer when you're running low temperature ALD aluminum oxide at 33 degrees. So these take very long cycles. The properties aren't as acute as they are at higher temperatures, but the good news is that this is possible. So when we apply that to roll, we have a different reactor design, and so roll really allows for cost-effective coating of polymers because we can just sit there and crank them through. So there's really a couple different methods in order to do this, and so we can create zone of reactants, like here in the scrolling substrate. Notice we have precursor A in the top of the reactor, precursor B in the bottom of the reactor, and then we've got this N2 purge condition. So instead of pulsing A, pulsing a purge gas, pulsing B, pulsing a purge gas, we effectively are running those cycles by actually taking the film and running it through precursor B, through the purge step to precursor A, back through a purge step through precursor B. And so the number of these spindles here will determine how many cycles of ALD you're actually doing. The trick is to really hold these precursors in these static volumes and create this dynamic gas window right here to keep the precursors from mixing. But literature quotes that this reactor, that's a industry reactor, can actually run at about 60 meters per minute. So that's pretty fast. We're running 60 meters of material a minute to coat. So that's like a high volume process. Mind you, we've only done 3 ALD cycles because it's only gone through these AB precursors 3 times. Another method to do this is the rotating cylinder. So here we have a cylinder here that's encased on a drum, and on a mandrel, and you just wrap your polymer or whatever on this drum, and you spin this thing. And so as you spin it, it goes through the A precursor, then it goes through an exhaust step, it goes through the exhaust, then a purge, an exhaust, and then a precursor step, and then a purge, and then an exhaust. And so as you spin this around, we're actually going around and getting different precursors and pulses and purge steps as I spin it. So there's a unique channel for each one of the delivery precursors and the exhaust. So in one rotation of this drum, you get 1 ALD cycle. So it sort of simulates roll-to-roll, but you can actually do a lot more cycles just by spinning this thing around as many times as you'd like. And this can run at about 300 meters per minute. So if you needed to have one piece of material that you wanted a lot of deposition on, you could use this rotating drum or this rotating cylinder process. So that's really all I had to say about the reactors. And so I'll just take a couple-minute break and check in with my assistant to see if there are any questions. So please hold. Take a break, go get a drink. And we'll start up again in about 5 to 10 minutes. So keep your eye on the clock, please. So there's a question from Raj, and he said, how do we dope metal oxides with metals, say hafnium oxide with manganese or molybdenum manganese in ALD? Well, that's going to be tricky because usually you would, if you're going to try to dope a metal atom within a metal oxide, that dopant metal atom would probably want to be oxidized also. So I think that might be very tricky to try to get. I think that's what you're asking, is how to get a metal atom inside a metal oxide composite. So I think with ALD that's going to be very, very tricky because you might just oxidize the metal, the manganese metal that you're talking about wanting to put in there. Mark, you said that I mentioned nucleation can impact the surface roughness. Are there any other conditions such as incomplete coverage that might impact roughness? Well, what else can impact roughness is as our crystals, as hafnium, for example, will go down amorphous for a certain thickness region. But then, as I start to grow more, I actually start to grow grains, and the film starts to become polycrystalline. And as it gets polycrystalline, then I actually start to make the surface more rough as I start to favor more crystal planes than other crystal planes. So you can see a film get more rough as you do ALD as it moves from a amorphous state to a crystalline state, such as hafnium oxide does. So that impacts surface roughness. And then Dimitrios, slide 16, why does the bottom have a thicker layer than the middle? And it's because the ALD chemistry, that was a through membrane. That anodic aluminum membrane was a through membrane. So we're doing deposition on both the tops and the bottoms. It's really about what happens in the middle. That's where we have to work on most of the diffusion, most of the molecular flow diffusion to get that deposition to happen in the middle of that structure. So the tops and the bottoms should be equal. It's the middle that'll be the difficult to etch. So even as my pulse goes through the reactor, yeah, it'll coat the top of that anodic alumina, but it'll also coat the bottom of that anodic alumina at the same time. Just because it's facing the other direction in the reactor doesn't mean it doesn't get coated. How would one activate high aspect ratio materials to better ensure starting layer of ALD? Activate high aspect ratio. So that's something to think about. That's a tricky question. That sort of boils down into like the nucleation of the film. How would I get a better nucleation of film on a high aspect ratio? And so some things you could do is maybe you could try to use ozone, and maybe you could ozonate the inside of the trench to maybe put these functionalized OH groups on the surface, which would be the reactive handle that you needed for deposition. But when you get down to brass tacks, it's really going to be, you're going to have to wait a long time to get that chemical to move in and out of those trench-like structures. So to activate the high aspect ratio would just sort of be more of a nucleation question, I think, maybe, than how to activate that surface inside a structure. But that's a very interesting question. Okay, well, that is it, I think, for questions. Yes, that's it for questions. So that's our break. And so I'll have one more plug here. Again, we have our area selective ALD conference. It's happening at the end of May. Very exciting stuff. We've got our ALD 2018. That's in Korea, if you happen to be there. That's going on. And I guess that I should also mention there's a atomic layer etching component to that ALD meeting as well. So you get, you can deposit your films and remove them, and then leave with nothing from that meeting. And then we also have our big 65th annual, or our 65th International Symposium and Exhibition, and that's going to be in beautiful downtown Long Beach at the end of October. And again, I will mention that there is the ALD atomic layer etching webinar that's going to be on June 13th, and that's going to be taught by Steve George. It should be an excellent class, and you can register that at the AVS site or use that link. And again, I'm teaching this AVS short course, but in a much greater detail in June, on June 15th, in New England, outside of Boston, and that's sponsored by the New England chapter of AVS. So with that being said, I'm going to get started again on our final topic, and that is ALD reactors are next to our final topic, the theory and design. So let's talk about ALD reactors, the theory and design, and the different reactor types, whether it's a laboratory or a production reactor. I'm hoping a lot of you would be interested in actually building your own ALD reactor, and if you are, I recommend you go to the reference by Elam in the review of scientific instrumentation, because that'll tell you how to do it. And also, if you're going to build your own laboratory reactor, make sure you can get the ALD of aluminum oxide chemistry to go first. Don't try any exotic chemistries. Get your reactors tuned up with ALD aluminum oxide using trimethyl aluminum and water. And once you have that done, then you can move on to more exotic chemistries. So that's a little bit of advice. So let's talk about the theory and design of reactors. So the Suntola patent back in 1977 described a rotor reactor that actually moves the samples across the precursors and not necessarily pulses the precursors across the substrate. So here's the actual clip from the patent. And so you can see here he has a chamber, and he's got this mandrel or this platen right here that gets rotated, and he's got like precursor A on the left and precursor B on the right. And so what happens is that this platen actually will rotate. And as it rotates, it'll go across precursor A, then it'll have a purge step, it'll go across precursor B, and then have a purge step. And all the while, we're sort of flowing gas into this and then pumping through the bottom. So here's a top-down view to the right of that, and you can see where you put your I don't know what they are, 2-inch wafers or 4-inch wafers back in the day, and as you spin this, you will get the ALD chemistry to happen. And so this is very interesting because this is actually considered a spatial ALD tool, which are now back, they're back in style, these spatial ALD tools. Rather than pumping or pulsing and purging, we're now moving, in the semiconductor industry, we're now moving substrates around shower heads to get the ALD chemistry to happen and not just pulsing and purging through a shower head. So here is a photograph of the first production ALD reactor. It's the microchemistry F120 reactor, and we sort of went over that in a little bit of detail about how it uses solid precursors. So here would be your injection manifolds for your gases, and then your exhaust would be on the other end of this, and then you've got some computer control here. The solid precursors are basically placed inside the reactor, and it uses that gas valving or these gas windows to control the pumps, the pulsing and the purging of the reactants. Now, we talked about, this is the same sort of cartoon of an ALD reactor, and we talked about reactive sticking coefficient, we talked about chemical exposure, we talked about flux and the vapor pressure of the reactant in the gas. And so what we want to do is we want to flow a nitrogen carrier gas down here. We want it to interact here with the vapor pressure of our liquid or our solid or our gas, and then we want it to transport and carry that down across our sample. So what we want to, really the question we want to ask ourselves is, what's the most efficient flow and pressure we need in order to get this vapor pressure up out of this precursor into the flow and then down across our solid. So typically, if we want to deliver our precursors, we can do it through a cross flow reactor, which I've shown here, where the reactants go across the flow of the sample. We can do it in a shower head, where we have the shower head design, where we actually flow it right on top of the of our substrate sample. Heating we can do in two different ways. We can externally heat the whole reactor by wrapping this in heating tape. It's all at the temperature of the deposition, and just by convection and conduction and probably radiation, we heat the sample to the desired temperature. So that's externally heating the walls of the reactor. It allows for efficient flow. Things don't sit and absorb on the surface for a while. You get clean pulsing and purging. The other way is to have an internal hot stage, where I have wires that come into this reactor and I physically heat the sample. Probably the best reactor would be a little combination of both, where you'd have a warm wall reactor, but also have an internal stage where you can heat the sample and tune that to whatever temperature you'd like. Now, precursor delivery, we know that we can use an external bubbler or for solid or liquid precursors, or we can use an internal boat of precursor like the F-120 does. And again, I mentioned that higher aspect ratios use larger chemical depositions for conformal deposition. So let's drill down into the conditions necessary here in order to get the right pressure of the reactor so that we get the best delivery of material. So we know that our reactor, we want it to be in the viscous flow regime, which is everything above like 500 millitorr. You could probably push that down to 250 millitorr, but you want your reactor pressure to be 500 millitorr. Now, if my reactor is too high in pressure, then I can't get the vapor from my precursor into the reactor. So if I run my reactor at 100 torr pressure and the vapor pressure of my water pulse is 20 torr, that 20 torr is not going to get sucked into the 100 torr overpressure. So somewhere there has to be a fine, a middle ground between getting the flow of the reactor to work right, high enough to get the viscous flow of the reactor, but then low enough to actually get the carrier injection or get the precursor injection into the flow. So if I have, let's see what it's, trimethylaluminum water, or about 1 × 10⁴ Langmuir. You need 1 × 10⁴ Langmuir of exposure for this. So if we look at the reactor tube pressures, what pressure do we want? So we want the reactor tube pressure to be high enough to flow viscous flow. So here our reactor condition has to be higher than 0.23 torr, which I sort of mentioned. I said 0.25 or 250 millitorr. And then, of course, there's a geometric factor here where our Knudsen number has to be less than 0.01, and that has to do with the diameter of the reactor and the mean free path of the molecules in the reactor to ensure this viscous flow condition. So this is the lower limit of the pressure that I want to run my reactor. Now, the higher limit of the pressure of my reactor is that I want my vapor to get sucked into I want the vapor from my precursor to get sucked into that carrier gas flow. So where does that happen most efficiently? Well, that happens most efficiently at this thing called sonic flow. So sonic flow is when I take my vapor pressure and I divide it by 2, essentially. So anything above that value, I will have sonic flow of my chemical precursor into my reactor. So so that sets the conditions of the upper limit of pressure of my reactor and the lower limit of pressure of my reactor. So with aluminum oxide, that have vapor pressures about 10 to 20 torr, I want to run my reactor somewhere above 0.23, 250 millitorr to assure that we have viscous flow, but I want to run it below 5.8 torr so that I can get the sonic flow of my 10 torr or my 20 torr vapor pressure of my TMA and water into the reactor. So there are certain reactor conditions that you want to flow your reactor. Typical flow rates depend on the reactor that you're using. You can 25 to 500 skims maybe for a flow reactor in a laboratory, but in production, obviously, you're ramping things up to the liters per second or liters per minute type of thousands of skims in those reactors just because of the larger size of them. So those are the conditions for flow reactors. So let's talk about laboratory reactors. I mentioned that we have a hot wall reactor where we can just take a tube, we wrap it with heating tape, we wrap it with foil, we plug it into a variac, we monitor the temperature somewhere, and then those heats our samples. So this is again out of Jeff Elam's review and his reactor design and review of scientific instrumentation. I strongly recommend you look up that reference. But here's his manifold, his gas manifold with trimethyl aluminum water. Here's his gas switching valves, which are actually, I explained in more detail on a previous slide. And then we just have our flow tube. The flow comes down to a mechanical pump. And so we flow a certain amount of gas in there. And the way we determine what the pressure of our reactor is we use this throttle valve. So if I turn that throttle valve down, the pressure of the reactor goes up. If I open it, the pressure goes down. So I can vary the pressure in the reactor by this throttle valve. And so in his reactor, he ran it typically at 1 torr of pressure, a flow of about 200 skims, and the flow velocity of 200 skims through this 2.5-inch or 3.5-inch conflat was about 2.5 meters per second. So here's your flow tube, and you can imagine if this gas is flowing at 2.5 meters a second, it's whipping through the reactor. It's going very fast. And since I've reached the sonic flow condition, then I know that these chemicals are going to be injected right into that flow and right down the tube. So hopefully that gives you some visualization of how the actual process works. And if you want to go back and have any questions about this particular kind of injection process, why don't you send me a question. So this is an ALD flow reactor. Here's a plasma ALD reactor. It's a laboratory reactor. Here we have a column. This is a remote plasma. So obviously it's going to be done at lower pressures. This is just a quartz tube that's wrapped with a wire with an RF generator on it. They're running at 13 megahertz. That's a typical plasma frequency that runs, but they're running at 1200 watts, which is pretty big. And their working pressure is really, really low. And so this was really used to grow tantalum and aluminum, titanium and aluminum metals, and tantalum metals using the hydrogen stripping reaction or the hydrogen plasma. So they generate this plasma in here. They have this solid precursor source, regrettably, for the titanium, I think it's tetrachloride, or tantalum pentachloride. And so they bubbled in there and they blew it into the reactor. It went onto the surface. And then they opened this gate valve. They exposed it to hydrogen plasma, and then they could grow this tantalum or this titanium or this aluminum film. Mind you that as soon as they took it out of the reactor, it turned into an oxide. So anything lower than 130 angstroms, I think it was, it would all spontaneously oxidize. So they had to go a pretty thick film, have the top oxidized to see that it was actually you're growing ALD metals through this ALD plasma reactor. This is a laboratory reactor at IBM. So the next would be an industrial reactor, and so I know that it takes time to perform ALD chemistry, but this reactor is by Sundew Technologies, and it was really designed to do very, very rapid ALD of aluminum oxide. And so the trick here is that here's your nitrogen purge that comes through the reactor and to the pump. But they also have this diversion line that comes down and goes below the sample right here, and then to the pump. So they purge their gas, which is fine. But then when they would want to do a reactant pulse, they completely shut off the nitrogen purge right here, and diverted the flow down to the pump down here. And so this does two things, which is pretty slick, is that it not only reduces the amount of nitrogen up here in this chamber, increasing the reactant exposure from this line, but it also adds this additional Venturi effect, which is this additional pumping capability, which draws the reactant out of here and produces a better vacuum to pull this down. So as they do this, they on a pulse step, they divert the nitrogen down here, which increases the reactant exposure, and you get this Venturi effect, which increases the pumping speed of the pump. And then when you purge, you're just naturally purging your nitrogen through the top. And so so this reactor is done to do very thick ALD aluminum oxide, primarily on electronic circuits if you just want to coat and passivate them. And so these ALD aluminum oxide cycles can be done in sub-second time scale. So you're really, excuse me, rapidly doing these half cycles and putting down ALD aluminum oxide very, very quickly. So I wanted to point that out as a very interesting ALD reactor design. The next is sort of in combination with doing a roll-to-roll. This is atmospheric pressure ALD or spatial ALD. And this is a kind of a unique design here. What I do is I have my substrate, and I'm moving my substrate maybe back and forth or maybe just through once. But I've got these channels here that I've cut into this piece of metal. And so one of those channels is going to be the B reactant, the other is going to be an A reactant, and the channels between them are actually nitrogen flow. And so what you're seeing here is that these reactants flow perpendicular to the page. They're sort of flowing forward and back, whereas the substrate is moving underneath. So we just have these long channels of reactants. They're separated by this nitrogen gas window, and then I can just move my substrate back and forth, left and right, and every time I do that, I get an ALD-AB cycle. And so this is done with aluminum oxide. Here's a better description of that on the lower left. Now, one of the problems with this is that this distance between the substrate and this head is very difficult to, especially if your substrate's flexible, it's difficult to keep that at a constant value. And if that varies at all, you can start to get mixing of your A and B reactants, even though you have this nitrogen purge in here. So it's a little bit tricky, but it was pretty unique at the time. And oddly enough, that it was really designed by a gentleman by the name of Levy at Eastman Kodak in 2008. And I really think that it really sort of transformed the mind of the ALD community to say, hey, we can really do ALD in a much different way. And so that naturally led to these roll-to-roll reactors and these drum reactors. And so even recently, because maybe the question that's coming up, that at the last AVS conference, I saw a talk that talked about an ALD print head, where you can actually print ALD chemistry on top of a substrate, kind of like a 3D printer, but it's using ALD chemistry to sort of grow structures and design them using a printer head. So you'll probably hear more about that in the future. So that's a very exciting development. So that ends this section. And so I'd like to get into surface analysis real quick, and I'll try to maybe finish on time or a little bit early. And so let's talk about surface analysis. Everyone probably that's on the other end of this camera is intimately familiar with surface analysis of ALD films. There's so many techniques that you can apply to ALD films depending on what you're looking for. I'm just going to choose three. I'm going to choose ellipsometry, quartz crystal microbalance, and X-ray reflectivity. But mind you, there is everything from in-situ techniques to ex-situ techniques, 4-point probe. FTIR is a very powerful technique. Mass spectrometry, Auger, XPS, SIMS, so many techniques you can use to analyze these films. But I'm just going to choose three, and we'll just sort of go through them in some short level of detail. Spectroscopic ellipsometry, that can be used inside a chamber or outside. It's the primary measuring tool for ALD films or any kind of films that you're growing. It really just uses elliptically polarized light that hits a surface, and then that elliptical polarization changes. It changes its polarity, and it changes its polarization, and you check that change in polarization with light. And so by knowing these known optical constants, you can determine the film thickness. Surface roughness can obscure the accurate values of thickness, and so sometimes using bulk optical constants as fitting parameters may not accurately fit the ALD film, because ALD films are slightly different than our bulk neighbor values. So, so I just wanted to point that out, that sometimes you have difficulty fitting these things, but ellipsometry's come a long way with spectroscopic ellipsometers and infrared ellipsometers. So This technique is a very powerful technique, and you should be obviously familiar with it on your end. The second is my favorite technique, is quartz crystal microbalance. It's an in situ technique that relates the oscillator frequency of this quartz crystal to the mass change that happens on it. And it's very, very sensitive. So small changes in mass will be small changes in frequency, and I can actually measure that. So it's actually so sensitive that you can measure the mass gain and mass loss of each of these ALD half reactions, which I'll show you momentarily. But QCMs are also very, very sensitive to temperature. So if you have a cold pulse of precursor coming in, you'll see a dip maybe in the quartz crystal microbalance, and that might just be a pressure transient or a temperature transient. And this plot here sort of shows the temperature coefficient as a function of temperature. And usually where you run ALD chemistry, maybe 177C. For aluminum oxide, you're on some sort of slope. But the good news is that they make all sorts of crystals out of gallium phosphate and other crystals that are temperature insensitive, or relatively temperature insensitive, or crystals that go way high up in temperature, like 300 some odd degrees, with minimal temperature instability. So QCM is a very powerful technique to use in ALD, and with the myriad of crystals that are out there for different temperature range and insensitivities, it will continue to be a very powerful technique. The third technique I won't elaborate on very much, but it's XRR. And the reason why I like this technique is because not only can you get the density of the film out, but you can also get the thickness out. And so I'm just not going to spend much time on this slide, but this is a typical XRR diffractogram. And these humps, the amount of humps that you get determine the film thickness, and where this sort of drops off, that initial specular reflection provides density information about the film. This is a very expensive tool, but it's also very handy if you have access to one for sure. So check that out. So those are 3 techniques that I wanted to go through. And so what I'm going to do now is just go through a quick surface analysis of aluminum oxide and go through what those look like. So aluminum oxide is an insulating material. It's great because it goes down amorphous and it has high breakdown voltage and low leakage currents. It's very well behaved chemistry. It grows at an angstrom a cycle, and low temperature deposition is possible. So these are the half reactions, which I won't go over due to time, but you have your trimethyl aluminum reacting with OH group to make this methyl terminated species. That methyl terminated species is the reactive surface in the A and B reaction. I react that with water to make OH, and then I plug that back into the A reaction, and I do this ad nauseum to make a film growth. So let's take a look at how aluminum oxide has been analyzed. This is a confirmation of the growth rate per cycle, the growth per cycle. As of using quartz crystal microbalance, we see we get about a 1.1 angstrom per cycle growth rate, growth per cycle, excuse me. That's in situ, but then we also compare that to ellipsometer, which can do much thicker films, and we get 1.2 angstroms per cycle growth per cycle. So here's 2 in situ and ex situ techniques, and they both agree pretty well. And 1.1 angstroms per AB cycle is going to equal 38 nanograms per square centimeter. So let's take a look at that in terms of the quartz crystal microbalance. This is my favorite quartz crystal microbalance slide because it really shows you the A pulse, the trimethyl aluminum pulse mass gain, and then the water pulse and half cycle. So you see the A half cycle and the B half cycle. Now, I was told by the author of this publication that this was an average of about 70 quartz crystal microbalance traces to get this nice resolution on this quartz crystal microbalance. But it really gives us a lot of information about it. We can see that the OH pulse puts about 3 nanograms per square centimeter on the surface. Now, that 3 nanograms corresponds to about 1 × 10⁻⁴ OH groups per square centimeter. Now, 1 OH group per square centimeter equals about 1 H group every 60 sites. So here we've been able to quantify what happens on that square centimeter just with this quartz crystal microbalance. The aluminum oxide ALD grows about 38 nanograms per cycle, and you can see a majority of that happens with the trimethyl aluminum pulse. And so it could be possible to control the dopants, depending on the dopant, in your metal film using atomic layer deposition. Another technique would be either mercury probe or 4-point probe. And so this was great work done by Marcus Kroner. And so here's different thicknesses of aluminum oxide films, but you can see that there's as I apply a voltage, it's very low leakage, and all of a sudden we start to see a current flow as there's different thicknesses of films. And so this is, what we're seeing here is this Fowler-Nordheim tunneling effect turn on these very, very thin films. So here the voltage is small, all these electrons are trapped on one side of the aluminum oxide, which would be a current density of 1 × 10⁻⁹ amps per centimeter squared, which equal about 1 million electrons running through a site in a second. So that's interesting, you can kind of visualize that. But as I increase the voltage, then this barrier actually changes form, it gets thinner, and I get these electrons to physically tunnel through to the other side. I like this because we're actually looking at tunneling responses inside ALD-grown films. The third technique would be FTIR. This FTIR is in difference mode, where I take the spectra that I previously took and subtract it from the spectra I presently took. And so what you're seeing here are the switchings of the surface sites. So here in a water exposure, this is the CH stretch, and I can see that CH stretch disappear, where over here I see that the ALOH stretch increases. But then when I do a trimethyl aluminum pulse, I see the CH3 stretches go back onto the surface, but then I subtract the OH pulse. So here in FTIR, I'm looking at these vibrational bonds, and I can see these things in subtraction mode, either being lost or gained on the surface. This I've already went over. This is the ALD of low temperature aluminum oxide deposition. You can just see primarily the density changes as I go to lower temperature. I'm not going to elaborate on that right now. And right here, the last slide would be Auger, in situ Auger. And what we're doing here is we're looking at aluminum oxide film on tungsten. So tungsten's a metal, aluminum oxide's an insulator. We're looking at how aluminum oxide nucleates and grows on tungsten. And so here would be the tungsten substrate. There's the signature tungsten Auger signal. It actually looks like a W for some reason. And so then as I do my water cycles and TMA cycles, I can see that my oxygen peak grows and my tungsten peak goes down. So there, my surface is evolving from a tungsten surface to an aluminum oxide surface. So this is really about watching the nucleation of aluminum oxide on tungsten. And and so I can get into greater quantification of this in my short course. So the last is, I've got four slides here, is the applications of ALD. And so I've broken them up into two camps, the surface modifications and structures. And so this is probably under structures, but I moved to the surface modification, is we can actually build these nanolaminates to make an X-ray reflecting surface. So if I have enough of these interfaces here, X-rays can come in and bounce or have a Bragg reflection off of these interfaces. And then we can just get this Bragg, if the Bragg angle is met, I can get this Bragg reflection of X-rays. And so this was a primary focus of the George group back at the turn of the century. And so we basically built this mirror. We did a lot of nucleation of aluminum oxide on tungsten of this. And his group built this mirror. Here's an X-ray cross-section of it. And so here we're bouncing X-rays off this, and so this is the XRR diffractogram of that. And we can see that we see this superlattice reflection at a given angle of the X-rays coming in and coming back out. And so this had a 90% reflectivity of X-rays that are like 1.54 angstroms. It was just remarkable work. And then they applied low temperature ALD and put it on Mylar so that possibly you could put it in outer space. I mean, it's just remarkable. So there's more detail of this at this publication down here by Francois Fabriguet. You can look into that in more detail at your leisure. The next application, which I think is pretty prominent, is lithium-ion batteries. And so what they basically did is they took, the lithium ions, you shuttle these lithium ions between graphite and lithium cobalt oxide, these two electrodes. And so if I take ALD and I coat directly on an ALD battery array with only 5 cycles of aluminum oxide, it's thin enough to create a conductive path between all of these little grains, but it's thick enough to somehow inhibit the corrosion process, but still allowing the lithium to shuttle in and out of this. And so this is capacity versus recharge cycle. So just by adding 5 ALD cycles directly on the electrode, you can see that it extends the number of charge and discharge cycles. And so this is still being actively pursued. The details of this are actively being pursued at the National Renewable Energy Lab in Golden, Colorado. The next to the last application we have is this catalytic alloy formation. And so you maybe want to control the alloy formation of catalysis materials to see if we can, make these bimetallic platinum ruthenium catalysts and see if we can use those for methanol fuel cells. And so the reason why I really like this is that, the name of the game in catalysis is surface area. And so here we have ALD coated particle ALD coating particles on top of a particle. So each one of those little black dots you see on that is a platinum ruthenium metallic alloy, but it's on top of a particle. So now you have this massive amount of surface area that you can acquire by putting a reactive catalysis on top of particles. And so this is very exciting stuff, which you wouldn't really be able to do with conventional techniques. And now the last application is the nanostructured templating using ALD. So we combine the low temperature ALD with conformally coating processes. So here we have this top-down view of this phase imprint nanopatterning process where I spin on a photoactive polymer. I cause an interference pattern to happen within this polymer, and then it polymerizes where my fingers are crossed, and then I wash out the polymer between my fingers, and I get this nanostructure across like an 8-inch wafer. Here's a side view of that. And so what I can do, this is polymer now, so it's temperature sensitive. But if I coat this polymer with low temperature aluminum oxide, I can actually stabilize this temperature aside from the polymer having a temperature sensitivity to it. So this polymer was coated with aluminum oxide at various temperatures until we ramped up to like 300 degrees C, and then this structure was coated with platinum ALD at 300 degrees C with 200 angstroms of platinum ALD. And this initial photopolymer, you couldn't take that up to 300 degrees C for platinum ALD. You needed to use this intermediate templating step of aluminum oxide at different temperatures to get to this step. So here we have this high surface area nanostructure that was made from polymer, but now has the conducting metal on it. So you can imagine making a very high surface area capacitor out of that. So that's the last of the application space for ALD in this webinar. And so I'd just like to end with my conclusions. And so ALD can be understood by really examining the root vacuum and surface science processes. It's a gas phase process. It's also a surface science process. So we needed to review those two subject areas. ALD is also a very powerful technique to deposit films, and really the ability to have thickness control, the conformality to code high aspect ratios makes it extremely unique amongst all the suites of deposition techniques. ALD can be deposited with thermodynamics, also with plasma-based processes. And today there's just myriad of elements and compounds that can be deposited with ALD. Now, mind you that their properties might not be what we want for a particular application, but it's very exciting that these exist. And there will probably be a lot more improvements to those in the near future. And so precursors can be gases, liquids, solids, or plasmas. All states of matter are involved in atomic layer deposition. primarily it's the application space that's growing in ALD. Every time you go to the ALD meeting, there's always somebody new that thought up something creative of how to apply ALD to something, whether it's clothing or whether it's hair color or whether it's acetaminophen or particles of aspirin, drug delivery, the whole bit. It's just remarkable. So I want you to continue to see ALD advance the exciting area of nanotechnology. So if you get a job in the semiconductor industry, obviously you're going to have an acute knowledge of ALD, whether you're building a quantum computer or whether you're building your FinFETs or what have you. So I hope you found this course instructive, and I'd really like to thank all of you for participating. And I encourage you to take the class either at the AVS meeting in October in Long Beach or sooner in New England on the 15th of June. So if you have any questions, I will take a couple questions right now. And again, thank you for your time. This will conclude the AVS webinar on atomic layer deposition. Thank you. Okay, so we have about a minute for questions. So let's take a look. Looks like Lydia uses hafnium oxide. Our trenches are now more narrow and deeper than ever before. We sometimes get a layer deposited and sometimes we don't. What parameter changes would you recommend we begin with? So sometimes you get a layer deposited inside your trench and sometimes you don't, I guess is what I'm hearing. I'd have to know really sort of the details of the aspect ratios and what you're trying to coat. Remember, hafnium oxide has this sort of this soft saturation to it. So you might see a lot of film be growing up on top of your structure and a smaller amount being deposited inside your structure. So if that's the case, I'd probably lower the temperature a little bit so that we would be more in a kinetic regime so that the reaction would happen more slowly. David says, thank you for the presentation. I was wondering why you could talk a bit more about stoichiometry. What's the best way to measure stoichiometry of ALD films? Well, probably the best method would be Rutherford backscattering, but that's an expensive technique. But also there might be other techniques. If you're doing nitrides, for example, you can do FTIR on that film, and you can look at your silica if you're concerned about the amount of hydrogen in your film, say. You can get a pretty reasonable number of how many hydrogens are bonded to silicon or nitrogen. So you could try that. That's a tough question, I think, because it's really about the level of sensitivity of what you need in order to get stoichiometry. And then Sudarshan, I think it is how you pronounce that. Any comments on safe handling TMA? Where to learn safe handling TMA? That's a good question too. I don't know if there's any acute procedure on how to handle TMA, but it is pyrophoric, so it'll react violently in air. It won't explode. It'll just catch on fire. So I would just make sure that all your valves are shut and just be very, very aware of the cautions. But I'm not clear of any safe handling. I wouldn't be too worried about it. Just be good about it, and you should be okay. And then also, what metals can be deposited so far by ALD? Well, that's a big question. There are a lot of metals that can be deposited by ALD right now. And I think that if you take my class in June, you'll probably get a much more comprehensive view of all the metals that can be deposited. And even when I teach my class, I'm never really up to date on the latest and greatest chemistries that are being applied in order for metal deposition. But I hope that by going over 4 different techniques of depositing elements, you have some greater idea of that a lot of metals can be deposited through ALD, single element ALD. And then do we have any more questions? Okay. Well, listen, ladies and gentlemen, if you're still online, I'm going to sign off now. So I really appreciate you taking this class. And if I see you in the future at the AVS conference or at the ALD conference, please feel free to introduce yourself. I'd be happy to talk more with you. So thank you very much.